this meeting caught me in the middle of a rare day of vacation, but I am happy to have this opportunity to welcome you to Cagliari, to this land of full of natural beauties, but also cultural heritage. Thousands of years of presence in the island, and not last, we are here together to contribute to continue the culture in this place. The Observatory of Cagliari is managing the big antenna, the radio telescope, 1 hour drive from there. It is not the last, but one of the testimonial of the culture in this place. And it is managed by the Observatory of Cagliari of the Italian Institute of Astrophysics. Of course, we are not only radio telescope, but there are many researchers that works in different fields, from astrochemistry to high energy, and of course, technology for the radio and for the high energy spacecraft. Just let me thank all the organizers and the people who worked for this meeting here in Cagliari, and I let you enjoy the NuSTAR 2022. Thank you.
So I'm just going to add my few words of welcome. It's hard to believe that it's been 10 years last week since NuSTAR launched. I can remember the moment very well. And it's so great to see a lot of new faces, people who have started using NuSTAR over the course of the mission. But I especially want to thank the organizers. Matteo Bachetti and Daniel Stern did tremendous amount of work to put together this exciting program. And I also want to thank Luisa Serra and the people from Cassiopeia for all the wonderful work on all the logistics. And I also just want to say that it's very fitting that we're having this 10-year anniversary conference in Italy because of all the contributions made by Italy through the Italian Space Agency. Those of you who don't know, a lot of the software development for the analysis tools that you use was done at ASDC, and we still use the Italian Space Agency ground station in Malindi to get the data down and to your laptops. So it's really nice to be here. And without further ado, I'm going to turn it over to Matteo, who's going to chair this session.
Yeah, sorry, bugs. This is the kind of things that happen when, you know, you think you've done everything possible to avoid, and then your new computer, apparently infallible computer, will let you down. Anyways, the first session is about welcomes and mission status. So the first speaker today is Carl Forster, who will give us the status of the observatory. Please, Carl, the floor is yours.
Thank you, Matteo. I hope everybody can hear me. Buongiorno, amici. I'm very excited to present the observatory status for NuSTAR. I'm speaking to you from the NuSTAR Science Operations Center at Caltech, and I'm always happy to give a NuSTAR status report, mainly because 99 times out of 100, if you ask me, NuSTAR is nominal. We are very fortunate to have a very stable spacecraft and instrument. There's been very few issues over the last 10 years. But very, very briefly, I wanted to run through some of the subsystems. As you can see, there are no concerns for any of the spacecraft subsystems. The LeoStar 2 spacecraft bus has no consumables, so we have no concerns about cryogens or any thruster fuel. We performed evaluation of all the subsystems last year as part of our preparation for the senior review proposal for this year. And as part of that, an evaluation was made of the battery end of discharge voltage. And it shows normal aging. This was the only system that Northrop Grumman, the builders of the LeoStar 2 spacecraft bus, suggested that we look in detail at. And in fact, based on the aging that we've seen over the last 10 years, we've got at least another 20 years before there are any concerns with the batteries.
Carl, are you showing the slides?
I am showing the slides. Can you not see them?
No, we see only the first one.
Okay.
Oh, okay. Yeah, but you're not presenting them, right?
I was presenting them, but I guess they didn't come through. So I'll do it in this format. So
okay,
here we go. Let me just quickly go back here. So these are the observatory subsystems. Everything is nominal with no concerns. And if we go through and have a look at the other systems on board, the instruments, we did have some concern about additional heating at the rear of one of the optics at Optic 0. This was seen a few years ago, about 5 years ago, and the conclusion was that there's probably a small tear in the thermal insulation that covers that optic. The temperatures that it reaches don't come anywhere high enough for any real concerns for the optics, but just out of an abundance of caution, we try and perform observations where the sun is within 130 degrees of the target. This introduces a minor scheduling constraint. And in fact, when we do observe where the rear of the optic is cold, there is some calibration adjustments that were needed for essentially the increased effective area on FBMA. That's included in NuSTAR DAS and can be used if needed, if you see a difference between the two telescopes. We also, just last year, as part of our evaluation of all the systems, we took images from all the star trackers on board NuSTAR. There are 3 star trackers on the spacecraft bus that control the attitude that feed into the attitude control system. And there's one other additional star tracker that is mounted on the optical bench, co-aligned with the X-ray optics called CHU4. And what was discovered was a small sort of low gain area in the center of the field of view of that star tracker, the central 1 degree. And this is caused by the solar observations that we've been performing during the mission. But there's still plenty of field of view for that star tracker to match to star catalogs. And so the performance remains normal, and we don't have any concerns there. But what we did implement this year was a new constraint for observations where only solar observations are allowed at less than 20 degrees from the sun. So the one system that we have been keeping a close eye on is the laser metrology system. We discovered fairly early on in the first few years of the mission that the intensities of the lasers were declining. And for laser 1, it was declining fairly rapidly. So a number of adjustments were made trying to slow that decline in intensity. And eventually what was found was a change in the duty cycle of the lasers, the on-off cycle of the lasers, stabilized both lasers and significantly reduced the decline in intensity. And at the current rate of decline, that system should be nominal for at least another 10 years, but we can make further adjustments to extend the laser lifetime past that. But in fact, at the same time we were examining possible changes to the lasers, work was begun on the development of a predictive model for master motion. This was led by Hannah Earnshaw at Caltech. And what was developed was an algorithm that estimates the position of the non-functioning laser based on the historical sort of motion, the flexing of the mast. And this is now ready to be implemented. And so the development is underway at SSTC of adjustments to NuSTAR DAS. If one laser fails, we can quickly switch over in NuSTAR DAS so that we can use the data from the other laser to estimate the motion of the mast motion. So in summary, all the observatory subsystems are nominal. One other thing I wanted to mention, of course, was the orbit altitude. The NuSTAR orbit has declined by about 20 kilometers over the last 10 years as we went through the previous solar cycle. So we've been in the solar minimum for the last 4 or 5 years, and we're now just moving into the next solar maximum. And we can expect the altitude of NuSTAR to drop by another 20 kilometers or maybe slightly more, depending on the solar activity heating the Earth's atmosphere and introducing drag on the spacecraft. But we have quite a leeway there, and we feel that if we can get past the next solar maximum, we're good for even a few more years past that. So I don't think we have any real concerns about the orbit altitude. So I really wanted to mention all the amazing work that's been done by the teams that make up NuSTAR. We have a number of groups that are involved in mission operations, as well as running the General Observer facilities. The mission operations team at Space Sciences Laboratory at UC Berkeley operates NuSTAR spacecraft along with a number of other spacecraft as well. It's a multi-mission operations center. And they're the ones that communicate with the spacecraft, organize the ground station passes, and basically host all the raw data and telemetry from NuSTAR. Then, of course, we have the Science Operations Center here at Caltech. We have the calibration scientists, as well as the scientists involved in operations. And we also press gang all the postdocs here on the high energy group to perform quality assurance on all the data. So they look at every single observation that NuSTAR makes and basically produce reports on all those observations that gets fed into the archive. We also have a number of joint programs as well with NASA and ESA spacecraft. NuSTAR observing time is available through Chandra, XMM, Swift, NISA, and Integral calls for proposals. And we have a reciprocal relationship where time on the XMM, Swift, and NISA is available in NuSTAR AOs as well. And of course, we have the NuSTAR DAS developed and maintained by the team at SSTC. And as Fiona mentioned, ASI also provides primary ground station in Malindi. And looking into the future, we're hoping to also fold in joint programs potentially with IXPE and with GRISM as well. The General Observer facility is based at Goddard Space Flight Center, and the team there basically host the archive at HESAC, the NuSTAR archive at HESAC, as well as organize and run all the NuSTAR proposal cycles. And they also host all the analysis guides, as well as the FAQs and the help desk as well. The team there was also involved in a anniversary cartoon that was put together, and hopefully you'll get to see that sometime during the conference. So really what I wanted to say is a big thank you to all the teams that are involved in NuSTAR. It was a significant effort to actually operate the mission in an efficient manner, and it's a highly productive spacecraft. And I'm very excited to hear all the talks during this conference. And I just wanted to emphasize that we are very lucky as a community to have a scientific instrument that is stable, well calibrated, operationally efficient, and highly productive, and is also very responsive to the needs of the community as well. So I know that you're probably looking forward to a coffee break in about half an hour or so, but for me, I'm going to say saluti. Thank you.
Thank you, Carl. We have time for a couple of questions. For questions, please come to the microphone that is not there, but will be put there in a second, if any. Zoom people can raise their hands and.
Yeah. And I'll be keeping an eye on Slack as well if there's any questions there.
Yeah.
Hi, Carl. Can you hear me?
Yes.
Hey, Carl, it's Dan.
Hey, Dan.
So what is the critical altitude that NuSTAR plummets to the Earth?
Yeah. Well, it won't plummet to the Earth. It's really a concern that the attitude control system will be able to manage the drag on the spacecraft and really control the momentum. And we've been told that's going to be at around 550 kilometers, maybe 540. But it's very uncertain. We may be able to survive lower than that. But I doubt we'll get down there for the next 10 years at least, maybe a little bit longer, unless the solar cycle really does become very active. Yeah.
Hi, Carl. Can you hear me?
Yes, I can.
All right, it's Aaron.
Hey,
what
Aaron.
do you think the chances are of having a 20 years of NuSTAR meeting?
I think very good. I think there's an excellent chance of having a 20, and I'm sure when I give the status report, probably some from my retirement home somewhere, it'll be nominal as well.
Thank you. Hi, Carl. Thanks. This is George Younes. In your senior, sorry about all the TOOs. So in your senior review report, the committee praised your work on transforming in a way NuSTAR to become a TOO instrument. I'm not sure if I read it correctly, but could you talk a little bit about that?
Well, when we first started looking at the prime mission for NuSTAR, the plan was to have 2 TOOs in 2 years during the prime mission. We've very quickly realized that there were going to be very many more TOOs there. So it really comes down to producing a schedule that has enough targets that can be replaced at short notice. Sometimes that works. In the past, it's worked very well. What we've been finding in the last few years, though, is that we've had an increase in the number of coordinated observations. So now more than half of the observations that NuSTAR performs are coordinated with another observatory, either a space observatory or a ground observatory, and those really can't be changed on short notice. We also find now that more than 3/4 of NuSTAR observations are time constrained. So in order for us to enhance our TOO capabilities, we're going to have to do some serious work with the planning system to be able to quickly turn around and make changes that don't have any sort of large downstream impacts on the observations. But this is the plan moving forward. Yeah, we'd like to increase the number of TOOs and also the number of joint programs as well.
Okay, thanks, Carl. Thanks a lot. Round of applause, and we go on. If there are more questions, of course, there's Slack, and we can continue there. Now I'll leave the floor to Christine Madsen for the calibration overview.
Hear me? Oh, here it comes. Here it comes online. Okay. So the moment I show this slide and it says calibration overview, probably most of you people are going to start glaze over and take out your laptops and check emails. So I'm not going to talk about that too much of it. Instead, I thought I'd talk about 10 years of NuSTAR mysteries. And they are a little bit, as you saw, they're a little bit detective work. They're a little bit like Clue. And the reason is you have built the instrument, you've sent it up. So when something strange pops up in your data that you know is probably instrument related, you should be able to figure this out. And I'll show you that we do, in most cases, we do figure it out, but there are still some mysteries left. And at the end, there's one particular one that we probably would like to, it's been around for a long time and we would like your help. Maybe one of you can solve that mystery for us. So I'm going to talk about a couple of mysteries, the biggest ones that we have encountered. And one of them is the mystery of the streak. John Tomczyk, I don't know if he's here. Is he here? No, I don't see him. Okay, so John Tomczyk would be very familiar with this because it turned up for the very first time in the NORMA survey, which you see in this picture on the right. We saw it as recently as last week, but it's not common at all. We've seen it maybe a few dozen times. When we first saw it in the NORMA survey, which is the one you see on the right, we were very confused about this thing that was sticking in at the edge of the detector. And when you can't see it very well, but you can actually see that there are different locations, and it had a distance in terms of absolute coordinates on the sky that was over an arc minute from each other. So if you go naively and you calculate a parallax for that, you get that whatever object created this could be no more than 2 kilometers away from your observatory. And that already goes, okay, that's really strange. And we came up with some really crazy theories, and one of them was developed over lunch. So we went there, you know, typically when we have problems, we sit and we eat lunch at Caltech, and we talk to other people about it. And there was Tom Prince eating lunch with us, and he said, you know what, there are these relic Russian satellites with active reactor cores on them up there. Maybe it's one of these. So we spent a frantic day or two trying to figure out if this was a Russian satellite with an active radioactive core that was somehow emitting as it was going past us. It's not. You may be sad to hear that. The second clue came when we did a Galactic Center survey, and we discovered that there were more multiple streaks. And when we then actually made a mosaic of these of the center, we saw the 2 streaks, and they had a common center. They were pointing towards the same location. So this is what you see there on the left. And if you take an integral image at that point, we hadn't completely surveyed the galactic center. So there is the integral image, and you draw lines from your 2 streaks. They intersect at the great annihilator. So that was the second clue. And the other was that there is exactly 60 degrees between these 2 streaks. And that immediately triggered I said, oh my God, it's the optics. Somehow it's the optics, because the optics, as you can see, they're built. Oh, there's my cursor. Good. So they're built such, they are segmented pieces of glass, and they cover 30 degrees. A segment covers 30 degrees. And we have a spider, as you can see in front of it, and that covers 60 degrees. So there are actually every 60 degrees, there is a gap between the mirrors. So there's 2 segments, and they don't quite match up. As you can see, there's this double, these purple things are, they are spacers that keep the mirrors down. And so between these 2 spacers, there's actually a gap. So what we were seeing is actually light from the great annihilator that was coming straight down the barrel onto the detector. Okay, so the other mystery was the complex detector mystery, as I call it. We started seeing this pretty early on, but not consistently. And what we would see would be very complex backgrounds. Sometimes we'd see a really bright detector compared to the rest of them. We'd see them in not the same detector. It would be a different detector. You'd see some very complex now we're getting feedback. Some very complex detector backgrounds. And this actually, it took a very long time for us to figure out what the hell this was. I think it took almost 4 or 5 years before we really realized what this was. And if you took, this is a little hard to see, of course. If you took the spectrum of different pieces of them, and you then took the ratio of it, you could see that there's this very distinct, it looks like an absorption of some kind. And that was sort of where it triggered, okay, we're seeing absorption of some kind, which then points towards it has to be somewhere close to the detector. Somehow you're getting light in and it's absorbed by something. So we have these, so here's an expert over on the left. You can see this is my notebook trying to figure out what the hell this is. So I was looking through all the possibly geometry. So what you see over there is these are the aperture stops that's supposed to prevent stray light from coming into the detector. And what these aperture stops were supposed to be, they were layered by aluminum, copper, and tin. And they were supposed to stop all of it, except when you then went and you say, okay, what if I remove the tin? And sure enough, if you remove the tin, which is what you see down here, so this is the Crab's stray light spectrum. This piece down here is also the Crab's stray light spectrum, but it has been absorbed by just aluminum and copper, not zinc. So it turned out that somehow when we built these aperture stops, someone didn't put in the tin. It's still a mystery where the tin is. Is it someone took it home with them? Did it never arrive? Huh? Or it floated away. Well, there is, at the end, I'll show you that the most likely scenario for many of these things is something very specific. So, so it's very complex because, so you have light that comes in, gets partially absorbed by these aperture stops. Now, there was one bit that was really still confusing to me, and that was this bright, because the aperture stops are circular, but this thing is actually a square. Turns out that that is the very entry, so where the detectors sit at the bottom of cesium iodide shield, and the entry to that is actually a square. So that's turned out to be that part. So when we look at these, what we call absorbed stray light, because I don't know what else to call them, you can see that we have here these 3 aperture stops plus the can. So 1, 2, I can almost not see it. Okay, 1, 2, 3, and then the aperture stop. Sorry, then the can opening. And it's a complex layering of it where you have 2 layers where you can go to through 2 aperture stops or 1 aperture stop. And that gives you this very complex pattern. So we solved this. It's the missing tin where we just don't know where the missing tin is now. Then there's the low energy excess mystery, which also took us a little bit to believe, because first we got actually reports back from you that you were seeing an excess or a deficit in MPM in one of the mirror modules. Now, we started collecting them, and at some point, one of them was particularly bright. And that's this, that was one of these, and it was, sure enough, it was enormous, this difference. We already at this point knew that we had a rip in the MLI, and we could see that on the temperatures. At some point, the temperature started to become really low. So just to show you what the MLI looks like, it looks like this, and it's got these rip stops, as you can see. And that never occurred to us that the rips could be really large, but it turns out it has to be really large in order to account for this sort of excess that we see. So if you account for the fact that there is MLI missing at the backside of one of the optics, you can account for it. And it's a large percentage. You can see it's almost 40% of the MLI missing on the backside of one of the optics. There's another mystery too, is that it actually changes in magnitude. So somehow, and we can track this with temperature, because as the temperature, as whatever this rip is, opens and closes, flaps in an unknown wind in space. This is still the mystery here. It opens and closes somehow. And when we tell this to engineers, they just look at us stupidly, but the data still shows us that when it's cold, you get more photons through. When it's hotter, it closes up. So here is the big obscuration mystery. This is the one we've not solved. This happened about 3 months after launch. We looked at Sagittarius A*, and these are the 2 FPMA, FPMB. You can see left, right. These are just the light curves of them. And somehow on FPMB for 27 hours, we had an obscuration event. And I show you the picture up on the little picture inset there. That's actually FPMA from the entire observation. And there's nothing weird about it, except that we had this decrease in flux through. And we've tried to look at everything to explain what this is, and we have not solved it. Now, the most likely scenario that we've come up with is that it's a space monkey with a wrench that somehow has been up there wrecking havoc, taking away the tin, putting something in front of one of the optics or whatever it's doing to mess with us and pushing the lasers around. So there, and if you've watched Space Force, you will know that this is a possibility. You can actually have a monkey with a wrench in space. So I'll leave you with this last slide, which was actually what I was supposed to talk about, which is calibration updates. So this can be done really quickly, which is in the last 2 years, we have updated pretty much every part of the calibration. And these are small updates, they're not huge ones. So we've got gain, effective area, absolute astrometry, and as Carl talked about, and I just as well, there's the MLI correction on FBMA. So with that, I'll stop and take questions.
Thank you, Christine. We'll give space for the next session, which will be shared by Javier Garcia on ULXs.
Okay, it's my pleasure to chair this session. This is a last second split decision, so sorry, I'm unprepared. But this is a ULX session, and we'll start with Don Walton, who is going to give us an invited review on ULXs. Dom, I see you have 30 minutes. It should be 25 plus 5, if possible.
Maybe 40, maybe 45.
Yeah,
Yeah.
I will
Really
tell
agree.
you 5 before.
Awesome. I'm going to just move this while talking, if that's okay with everybody. Yeah, it's really nice to be here, seeing people in person again, actually having real meetings and celebrating 10 years of NuSTAR. So I'm kicking off the science component, I guess, and we're starting with ultraluminous X-ray sources. I'll explain what these are in a little bit. It's an area, I think, fittingly, that NuSTAR has really driven an awful lot of progress in, which I hope you'll see. It's a very NuSTAR and very observational focused review. So if you're into super Eddington theory or whatever, and I should stress there are lots of key observations of ULXs that have happened in the last few years that have come from multi-wavelength work or from other facilities. That's all really important, but I am really cherry picking the NuSTAR results today. Because we're sort of doing this 10-year retrospective, I thought it was worth starting with a reminder of sort of where we were at with our understanding of ultraluminous X-ray sources before the launch of NuSTAR. And it sort of comes down to this. So we know loads of different kinds of black holes, small black holes, endpoints of stellar evolution and X-ray binaries, big black holes, supermassive black holes at the centers of basically, I think, every major galaxy now. But we don't really know too many good candidate black holes in this, what we would call intermediate mass black hole regime, so maybe 1,000 solar masses, maybe 10,000 solar masses or something like that. And that is one of the reasons that people, originally speaking, I would say, were quite excited by this population of ultraluminous X-ray sources. Because just to sort of give you the sort of out of the can definition for what a ULX is, it's basically an off-nuclear X-ray point source seen in another galaxy that has a luminosity in excess of 10 to the 39 x per second. I say it's in another galaxy. It doesn't technically have to be. It's just that almost all the ones we see are. The reason this 10 to the 39 x per second number is important is that this is, broadly speaking, the Eddington limit for the sort of the typical 10 solar mass black hole that you see in an X-ray binary. And so going back to this sort of potentially postulated and missing population of intermediate mass black holes, there was a lot of excitement about these objects. So like they're intermediate in luminosity between normal X-ray binaries and active galaxies. Perhaps therefore they're also intermediate in mass. So perhaps these are this population of intermediate mass black holes. And there was kind of this long-standing debate prior to the NuSTAR era about whether that was the case, or whether these were somehow normal X-ray binaries that had found some way to circumvent the Eddington limit. And now it's sort of a win-win situation, I guess, scientifically, because both of these scenarios are potentially important for understanding bigger picture questions relating to things like how do you grow a supermassive black hole, particularly given that we're now seeing some really big black holes in the early universe. This is probably a little bit out of date now, but this is just a sort of an indication of the issues that are being faced. So we've got some pretty whopping black holes that we know already exist at about redshift of 6 or so. And what these curves show are sort of backwards extrapolations of what their growth would have had to have been like to reach that mass at that time, assuming Eddington limited accretion. So you either have to start with something pretty big already, or you have to grow at rates faster than Eddington. Now, the reason that NuSTAR has been sort of so key for the study of ULXs is basically because of this, not just the extension of the band pass above the kind of canonical 10 kV, up to 10 kV, sorry, covered by things like XMM, Chandra, Suzaku, all of these in their own right fine instruments, but it's really its imaging capabilities as well. And just to illustrate this, we've had, prior to NuSTAR, we did have high energy X-ray detectors before, but they tended to be sort of non-imaging or like only very crudely imaging. And so they would basically integrate the entire flux over a whole galaxy. And that's a problem for ULXs because they are very luminous in their own right, but they are usually not as luminous as the AGN in the center of a galaxy or something like that. So you really need the imaging capabilities of NuSTAR to see these things in a broadband sense. And that's what we were able to do basically for the first time when NuSTAR launched. So we had this quite early mission, fairly extensive program that we planned out to study a set of ULXs. And basically our plan centered on this idea, which is that we are pretty sure that we know, at least empirically, what sub-Eddington accretion looks like. So if these ultraluminous X-ray sources had turned out to be intermediate mass black holes, then we know what they should have looked like. And that's basically because we think the accretion process is fairly scale invariant. We see in both X-ray binaries and active galaxies this kind of disk corona, like to 0th order, at least this sort of disk corona geometry. I'm not going to go into detail about this because you're going to hear a lot more about this through the rest of the meeting. But basically, at sub-Eddington rates, probably we're expecting some kind of spectrum dominated by Paolo-like emission from the corona. So that's the sort of the 0th order prediction for the spectra that we should have seen had these been intermediate mass black holes. And you can probably tell, because of the language that I'm using, that is not at all what we saw. So we saw spectra, I'm showing you one, yep, there it is. Showing you, nope, it's gone, back, it's gone. Okay.
Your computer. Oh.
Maybe I will switch this. Great. Okay. Yeah, so we saw spectra that looked like the top panel in basically every single case we observed. You'll see later on, we went after a little sample of these things. And I'm showing you a comparison of sort of a typical X-ray binary and active galaxy that, kind of show you the sort of spectrum that we would have expected had these been intermediate mass black holes. And they really look different. The NuSTAR data turn over really quickly and fall away very steeply at high energies. So we were very quickly, because of just this spectral data alone, we were initially focused on spectroscopy, pretty confident that actually, even if we didn't quite understand how the physics of all this was going on, was working, we were looking at, can't use that anymore, super Eddington accretion. So sorry, this is a really old gag now, but it's still a fun one. This was absolutely slammed home by the subsequent discovery, and I would say this is still probably one of NuSTAR's most interesting discoveries to date, thanks to Matteo, of X-ray pulsations from M82 X-2. So all of a sudden, we've gone from like thinking, well, maybe these are intermediate mass black holes, to within a few years knowing that at least one is not a black hole at all, it's a neutron star. And the key thing about these is, this is not just any old ULX as well, this is a pretty damn luminous one. So this is something that's radiating about 100 times its Eddington limit, which is pretty awesome. Now, this all came about basically because NuSTAR was following up a type 1a supernova that went off in M82. So we always had M82 as a sort of target from the ULX program, but NuSTAR ended up investing so much time in this galaxy because of the supernova that we went even further. Not only could we see X-ray pulsations from the object, we could also sort of time slice the data and actually see sinusoidal variations of the pulse period, which is what happens when the neutron star is orbiting its companion. So you get Doppler shifts to the orbit being imprinted on top of the timing signatures. So we basically went from knowing very little in a real sense about any ULX to actually almost having a fully characterized X-ray binary system overnight, because we could say that the orbital period here is about 2.5 days. That places a limit on the mass of the companion as well. It's got to be bigger than about 5 solar masses. The only thing from a binary standpoint that we don't really know here is the inclination, so that's why it's just all limits. And then you could even go further and sort of correct out the orbit, and you could see that the neutron star itself is being strongly spun up. That's not a big surprise. That there's a huge accretion rate falling onto the neutron star here, and that's torquing it and spinning it up. So that basically discovery sort of changed the landscape, I would say, certainly within the ULX field, almost overnight. It was really, really amazing. Since then, we've gone on to find several more ULXs are pulsars. This has become a little bit of a sort of sub-industry almost, trying to find these things. We've got a set of 6 things that I would call traditional ULX pulsars. And unfortunately for M82 X-2, although it's still great, it has been usurped as the brightest neutron star anybody's ever seen by NC 5907 ULX1, which gets up to something like 10 to the 41 ergs per second, so a mere 500 times Eddington. We don't really, I would say we don't really know how that works yet, but anyway, still going. I do want to do a sort of quick honorable mention, because there is this sort of population of BE X-ray binaries that occasionally go through these very large outbursts that just about at their peaks touch 10 to the 39. Swift's JO243 is a very recent and very spectacular example of this. And so this has, among some parties, been called the first galactic ULX pulsar, and that's fine. I think there are some significant differences between these sources and the sort of the more traditional ones, but like I tend to view these as being some kind of bridge between the more extreme ULX pulsars and the regular X-ray binary pulsar population. These are definitely interesting sources, but yeah, I mean, we still need to understand, I think, the similarities and differences a bit, but just did want to mention these sources exist as well. So we've got 6. You might be wondering, are there more out there? And I would suggest probably the answer is yes. And this is something I've been doing for a little while. Several years ago, I put together this sort of compilation of the broadband spectra. It's not quite every single observation we had around 2018, but it's reasonably close. And certainly it's representative of what we'd seen, just to see what things look like in a sort of global context. And I hope you can see that whilst there are differences in how these different sources look at low energies, which is sort of often related to different amounts of line of sight absorption and stuff, in the NuSTAR band, where you really know and are confident that your spectrum is dominated by accretion processes, all of these sources look qualitatively similar, including among these 12 panels here, there are 3 panels that come from things that we know to be ULX pulsars. The other 9 are from things that we don't. We don't know what the accretor is, I should say. If you're interested, those are the 3 neutron star ones. I know a lot of you have seen this before, so I moved them in case you were trying to cheat. Anyway, so I think we have a general expectation that there are going to be more of these things out there. Right. So how does this work? We've got empirically a set now of very super Eddington objects out there. And it is possible to accrete above the Eddington. This is an observational talk, but I will show you a little bit of some of the sort of the basic theory just to frame what we've seen. The idea of sort of behind how super Eddington accretion works is that as you dial up the accretion rate, the radiation pressure becomes much more important. And so you end up sort of having what, while you might have a thin accretion disk at sub-Eddington rates, you end up having this sort of transitional disk at super Eddington rates, which is still thin out to some radius. We would call this sort of spherization radius, but then really starts to puff up, becomes a thick disk in the inner regions and creates some kind of more like funnel-like geometry and emits huge outflows because radiation pressure is now sort of in principle beating gravity. This kind of theory has been around for some time. There are analytical theories. I'm showing you one sketch from Dotan 2019, but this goes all the way back to Shakuris and Yaev. It's also supported, this kind of basic geometry supported by MHD simulations. So, these zeroth order sort of elements of super Eddington accretion are all pretty universally agreed on. A lot of this theory has been centered on the idea of super Eddington accretion onto a black hole, though. And so for these pulsars, what's important to remember is that you have magnetic accretion. So at some point, because you have pulsations, there has to be column. You have to have the magnetic field truncate the accretion disk and force things through column-like accretion. So the key question that we've been trying to understand for these ULX pulsars specifically, at least anyway, is basically this. So this point at which the disk truncates is called the magnetosphere. It depends on the magnetic fields and the accretion rate in some combination here. And the key question is the magnetosphere smaller than this spherization radius? If that's true, then these ULX pulsars should have sort of self-similar accretion flows to the black hole case. So even though most of the theory has been done in the black hole case, that's probably still fine. If that's not true, then actually these will have quite different accretion flows. And so all this sort of talk of like trying to learn about black hole growth in the early universe and stuff basically depends on whether this is true or not. So that's why we've been really trying to figure that out. And obviously one of the things that this is sort of that's critical here is trying to understand magnetic fields. That's quite challenging to do for these sources because, whilst they're very luminous, they are quite far away. So often the data quality is certainly not comparable to what you would get in a galactic X-ray pulsar or something like this. If you wanted to measure a neutron star magnetic field, though, your sort of first port of call would be to try and find a cyclotron feature. Basically, what happens is that the strong magnetic field quantizes the electron energy levels in the accretion column, and you get resonant scattering at certain energies that depend on the field strength. And I'm showing you a very classic example on the left from a normal-ish galactic X-ray pulsar, VO332. And basically what happens is you get these almost absorption-like, it's not actually an absorption process, but it looks like an absorption-like feature imprinted onto your continuum spectrum. And the strength, they're actually sort of a primary and a fundamental here. And the strength of the feature, the energy of the feature depends on the magnetic field. And we may have seen one in one of these ULX pulsars. It's a little controversial, so there are definitely different ways of interpreting this data. But if this sort of cyclotron-like feature is the correct interpretation for the spectrum it's seen in this NC300 source, then that would give us a magnetic field of about 10 to the 12 Gauss, which is pretty common amongst accreting X-ray pulsars, at least anyway, and certainly is not so strong that it would prevent a classic super Eddington accretion flow from forming. I will point out, although Murray's unfortunately not here, that there's a second potential cyclotron feature in a ULX, which is very different to this actually. So it's quite a narrow feature, and it's about 4.5 kVc and some Chandra data. And if that's really true, it's sort of proposed to potentially be a proton cyclotron line. This would be an electron cyclotron line, and that would apply a whopping field of something like 10 to the 15 Gauss. So we've got a bit of a scattered picture here. But at least in the case of NC300, we have independent, I would say, evidence that this super Eddington accretion flow is forming, because in addition to this potential cyclotron feature, we've also got evidence for a very powerful wind. And again, that's something that should really come from a super Eddington portion of the accretion disk. So this is work led by Peter Kosech. There have actually been several fast outflow seed in other ULXs, which has sort of mostly been work been led by Ciro Pinto. But for this particular case, Peter was able to find pretty solid evidence for something like a 0.2 C outflow. So that's pretty epic for an X-ray binary. This, I would say, also sort of provides independent support for the idea that at least in this system, we do have this super Eddington portion of the disk forming. Right. Where are we going with this now? Thinking about the spectra that we see from ULXs more generally, you might ask sort of, well, what kind of emission components are we seeing? And basically the fact that the data all sort of turn over in about the 10 keV range obviously tells you that the data is not, it's not sort of a power law continuum. And so it's become quite traditional, particularly in light of this super Eddington accretion sort of model, to actually start fitting the spectra at least below 10 keV with a sort of a couple of accretion disk components. And basically the motivation is that, you know, you might have a lower component, temperature component that comes from the outer disk here, potentially with some contribution from the wind. You might have some higher energy component associated with the sort of the hotter inner funnel. But if you do that, where you have sufficient signal to noise in the NuSTAR data, you almost always see, in fact, I think you always see now, evidence that the data, the NuSTAR data specifically, are requiring that there's some additional continuum emission above 10 to 15 keV or something like this. So, because I do remember like being asked at some point, would a super Eddington accretion flow still form a traditional corona? And so if any of these sources that we've looked at are black holes, I think the answer is unambiguously, therefore, yes, they still must form some kind of corona. But even more interestingly, in the case of the ULX pulsars, you can do phase resolved spectroscopy, and you can actually tell that this high energy component is associated with the accretion column. And you can take what you know about the ULX pulsars as something of a template and try and apply that to the sources where you don't know the nature of the accretor. And in every single case, a ULX pulsar-like accretion column actually can reproduce the high energy data. So it's a little bit of a provocative statement, but you could, based on this, suggest that all of these ULXs are neutron stars, even if we haven't seen the pulsations from them yet. We don't know that that's true, but it's fun to speculate, isn't it? So I put this up again, sort of partly to drive home this point, but also as a slightly clumsy segue into like, what have we been doing since all of these results that I've shown you? Because you know, a lot of this stuff was sort of up to and including 2018 or so. And certainly this like, spectral ensemble is a little out of date. And if I show you the full range of NuSTAR observations of ULXs that we have now, it looks a bit more like this. So we've done pretty well out of getting more telescope time. A lot of these panels are repeat observations of the same target, but we have expanded the sample of objects we've looked at in the last few years as well, quite significantly too. I want to highlight a couple of results that have come out more recently that show like this has been sensational progress over the last 10 years. But there's still stuff that we don't understand. So I'm going to pick out a couple of these bigger programs. And you know, it should be clear, this is a really like a collaborative effort. So NuSTAR has been heavily involved in doing these sort of multi-epoch now campaigns on a sort of subset of these sources. Often in coordination with things like XMM and Chandra and stuff like that. And so some of this will be covered by later talks. So Matteo in particular is going to talk about M82. So I'll just pick out a couple of oddities from these bigger campaigns. And the first one I want to show you is one of the ULX pulsars, NC7793P13. So we've been monitoring these to try and track the evolution of the neutron star spin. And actually, this is a particularly interesting case because there's this has a known UV companion, and you can see that the UV data are periodic. You can also see that the X-ray data are periodic. They are not the same period though. And from the X-ray timing that's sort of provided by XMM and NuSTAR, you can also get a constraint on the orbit. So you can put together this model for the timing behavior that includes, you can see this sort of sinusoidal curves here, both the orbit of the neutron star and sort of a long-term spin-up. And you actually find, weirdly, that even though, as you can see from the middle panel here, the X-ray count rate or the X-ray flux as we perceive it has varied quite significantly over the last few years, the best fit model to the timing data actually suggests a fairly constant spin-up rate. So the spin-up is not connected here to the X-ray flux. And this is something that Georgios has also seen using more swift and nicer data on this NGC 300 system that I sort of highlighted before. So that's quite odd. You would expect the spin-up to track the flux under normal circumstances. So that's quite odd. And what's also quite odd is that, like I said, the UV and the X-ray period here are not the same. They are very similar though. And actually, for the X-ray timing suggests that the orbit is closer to the X-ray photometric period. The UV photometric period is slightly shorter. So we have, if you take all of this at face value, a slightly suborbital UV period here. And I don't think we understand why that's happening. The second oddity is that in cases where we've been able to do sort of quite decent multi-epoch broadband spectroscopy, we have seen this sort of strange behavior that, you know, there's a lot of variation going on below about 3 kV, and then this all sort of pinches together and doesn't really vary very much above 15 kV or so. And if you take these kinds of classic models that have become popular, like these two thermal components and something else at higher energies, and fold those models through these multi-epoch data and sort of see what the thermal components are doing in the luminosity temperature plane, you find evidence for 2 distinct luminosity temperature tracks for this hotter component. And I would say we don't know what's going on here either. Like, positive luminosity temperature relations are not uncommon, but seeing 2 different ones in the same source is pretty unusual. So yeah, let me just do 1 minute looking ahead. Our future efforts could probably broadly be summarized with this slide. That's actually the original line from the film, but they had to cut 1 second out for the final director's edit. We really want to find more ULX pulsars. I mean, 6 is a very nice sample, but you always want more. Just as a way of sort of facilitating this, there have been a decent number of efforts to put together new ULX catalogs in the last few years. I'll shamelessly highlight our own one just here, which is tried to combine the latest data releases from Chandra, XMM, and Swift. And we have in here about something like 1,850 ULXs now. Most of these are too faint for detailed follow-up, but that's still a pretty nice resource. And so at a very rough back of the envelope guesstimate, we reckon there might be sort of 5, maybe even 10 more ULX pulsars that you could detect with current instrumentation in here, but you sort of have to be a little bit lucky about the timing of your observations and things like that. And you know, they're all highly variable, so it's not going to be an easy road, but there probably is more to find here. And just some general statements on where I think NuSTAR will continue to contribute, aside from just trying to find new pulsars. We're continuing efforts to monitor the known pulsars. We want to do a lot more of this multi-epoch spectral evolution, particularly see if more things do this weird behavior we've seen in NC 1313. And I didn't really talk about outflows very much because that's not something NuSTAR has been so involved in. But actually there is now detailed photoionization modeling that Chiro is doing, trying to account for the SED. And that's being driven by NuSTAR data at the highest energies. So let me just make one very brief closing statement as a summary slide, which is just to say that, you know, it's been a remarkable 10 years. And thanks to NuSTAR, we really do now know that some of these ultraluminous X-ray sources, even though we maybe thought they might have been intermediate mass black holes before, are actually powered by wildly super Eddington accreting neutron stars. So yeah, more to come, I hope, over the next 10 years. Thanks.
Thank you, Dom. Questions? We have time for maybe 2 questions. Matteo, I'm not looking at the online question. I don't see anything in Slack. Well, that's.
Oh. So the question is, what do we think about SS433? And that is very convenient because I had a slide on that and I took it out. Because okay. So this is a galactic, a very famous galactic X-ray binary that's not that luminous, but is sort of known from multi-wavelength studies to be a very highly super Eddington accretor, but we're unfortunately viewing it almost edge on. So NuSTAR did do a fairly extensive campaign to track, to spread 10 observations or so over the sort of the phase of its known 160 or so day precession period. And so this is work led by Matt Middleton, because one of the things we were interested in investigating is whether or not this is an edge-on ULX that has been speculated a lot. Now, because it's so edge-on, the X-ray flux we see from this thing is actually primarily dominated by the jets this system launches, so it's very low luminosity. But by looking at the variability, Matt was able to find evidence for what he thought was reflection from the backside of this kind of inner super Eddington accretion funnel, this sort of blue shaded region here. And based on some geometric modeling that he did, was basically concluded that if you were to view SS433 face on, you would indeed interpret it or infer that it would be a ULX. So I don't know if that was quite the question, but I can tell you that's what Matt found.
Okay, we have a question here in the audience from Victoria.
Thanks so much, Dom. Great talk. I'm going to ask a slightly provocative question just for the fun. So you mentioned that you can describe all the ULX spectra with accretion column models. How many non-ULX spectra can you describe with a similar model? So is it really like unique to ULX?
Well, okay. So going all the way back here, anything that's a bit Powell like these sub-Eddington accretion models would not work, because the ULX accretion column spectrum, you know, we make a very crude characterization of this as a sort of a cutoff Powell, but it has a very hard rise, gamma of about 0.6, and then a very low energy cutoff about 8 keV or something like this. So I don't think Powell law like this is absolutely not going to be described by a ULX pulsar like accretion column. So this approach would fail for these sub-Eddington systems. But of course, if you had an abnormally low cutoff, you would find it more difficult to distinguish.
Okay. We have one more question in Slack, but I'll ask you to please answer that in Slack because we're running out of time. So let's thank Dom again. Our next speaker is our conference organizer, Matteo Bachetti, and he'll talk about M82 X-2.
Hello, everyone, again. So I'm going to talk about measuring the mass exchange and the first pulsating ultraluminous X-ray source, M82 X-2, or should we put a question mark in there? I wouldn't, some people would, so to be fair, I will. Anyways, M82 X-2 was the first discovered pulsating ultraluminous X-ray source. It was exciting. It was a field that was not included in the original NuSTAR NuSTAR survey of ULXs, just because in that field there are 2 ULXs in 5 arc seconds. So it was quite complicated to actually model the spectra of these 2 ULXs. So they were excluded. But then a supernova appeared and made this observation possible. So we did, and we found pulsations. And I would like to stress that these sources were observed for many years before by other instruments, but no pulsations were detected. I guess in part because people weren't expecting pulsations, but also because this particular ULX has a very hard pulse fraction. Like XMM would have a really hard time to detect pulsations. Now that we have NuSTAR and we have a very precise spin ephemeris of the source and orbital ephemeris, we can also detect pulsations on XMM if there is a NuSTAR observation in really the same time frame. Otherwise, the end trials will kill any statistics. This pulsar has a 2.53 day orbital period, more or less high-mass X-ray binary-like. The semi-major axis is 22 light seconds. The mass of the companion has to be more than 5 solar masses. Maybe we can push it down to 4, but really not much. And there is a 60-day or superorbital period as well that was observed. We know that it's a high mass companion just by standard constraints on the inclination of the system. Given the semi-major axis, we assume Roche lobe overflow and we make calculations. And we know that the minimum donor mass can be 3.5 solar masses, but that would be in eclipse, and we don't observe eclipses. So we push it up to 5 solar masses, and then the probability of an inclination, which is much larger. We have a very large range of possible masses, up to 100 solar masses, where it becomes a little unlikely to observe them in the first place. A good thing about this source is that we have managed to characterize the orbit in such a way that we can make very precise timing studies, and we can test accretion theories to their very limits. I guess it's something we can do with very few objects with this precision, I think. Standard accretion theory on neutron stars will generally speak about 2 specific radii. The first is the magnetospheric radius, which is the one where the ram pressure from the disk is exactly balanced by the magnetic pressure of the rotating magnet. And so matter is captured and it starts creating these funnel-like structures on the magnetic pole of the pulsar. And then there is the core rotation radius, which is the radius at which the matter orbiting the star moves at the same angular velocity as the pulsar. Depending on the balance between these 2 radii, we speak about 2 regimes. One is the slow rotator, where the matter is inside the rotation radius, so it's orbiting faster than the star, and it's basically pushing on the magnetic field lines and accelerating the pulsar, giving spin up, so-called spin up. And then we have the opposite regime, which is called the propeller, where the pulsar is moving faster. So ideally is able to push away the matter so that matter doesn't fall on the pulsar. In practice, it's much more complicated. There are instabilities and there is accretion even during the propeller regime. And in this case, the pulsar is actually torqued down. It's spun down by this matter, which is orbiting slower than the pulsar. And then there's, of course, an intermediate regime, which is called the spin equilibrium, where these 2 radii are more or less the same, okay? Different theories will push it outside or inside in a slightly different manner with different parameters, but more or less they're the same, okay? in this particular regime, it's easy to estimate the magnetic field of the pulsar, because if you use those two equations, you can compare them and obtain an estimate of the magnetic field. Still, you have to be sure that you are in spin equilibrium, which is something that the first time you observe a pulsar, you more or less never know. Okay. To estimate the magnetic field, you need the rotation period, the rotation period, the mass accretion rate, and the mass. We have the mass with 1.4 solar masses, more or less. We know between 1.1 and 2.2 solar masses, something like that. And the mass accretion rate is the more difficult to estimate. Anyways, spin equilibrium. Is M82 X-2 in spin equilibrium? I'd say yes, we have proved it quite strongly, because we've seen it. We've seen this source over time spinning up and down while it was accreting. We have observations where the pulsar is spinning down while we're observing the pulsations. So this is pretty strong evidence that the source is close to spin equilibrium. So more or less the average mass accretion rate on the pulsar is more or less exactly balanced by the magnetic field of the rotating pulsar. And depending on slightly higher or slightly lower mass accretion rate, the pulsar will spin up or down, spin equilibrium. We've had multiple evidence of this. We have this long-term observation, but also short-term observations where basically the relationship between the luminosity of the pulsar and the spin up are far steeper than you would expect in the slow rotator regime. So it's in spin equilibrium. So wow, yeah, we have the rotation period, we have more or less the mass, okay, factor 2. What about the mass accretion rate? This is the most complicated thing, because people will just take the luminosity, divide by C, use the efficiency, and will say, okay, the mass accretion rate is this one. But it's much more complicated than that. This thing works in the sub-Eddington regime. More or less it works, okay? But in the super-Eddington regime, it is expected that there is this strong outflow, which will geometrically bin the luminosity, as we're going to see. And in this case, people think, I don't believe much this hypothesis, but I mean, there's serious reason to think this is at least partially true, that I don't believe this exact parameterization. I want to be clear, not the fact that there can be beaming or geometrical beaming in this way. In this case, the luminosity is pushed far more than a standard linear relation with a mass accretion rate. There's a quadratic relation in this case. So the mass accretion rate you estimate from the luminosity is much lower than you would expect in the sub-Eddington regime, okay? So geometrical beaming is easy, okay? You have these two walls of things, of winds given by this super-Eddington flow, and then you'll have luminosity illuminating, you have the luminosity of the source illuminating these walls, and matter will be reflected, so you have it geometrically concentrated, and you have beaming. As Dom said, there's another way to obtain super-Eddington luminosities, which is including high magnetic fields. There are multiple ways to model this. It's probable that it's not a high dipole magnetic field, but it's mostly a high multipolar magnetic field, which is dominating this flow in the close proximity of the neutron star. Okay, and it's altering the Thomson cross-section and allowing for much more matter than expected to fall into the neutron star and illuminate. It's an ongoing debate. I'm joking about it. People are pretty decent. It's going on for a while now, and it's pretty fun, I think. Anyways, mass accretion rate, we've understood that mass accretion rate estimated by the luminosity is not, is not clear. So one thing we've tried to do over the years was to directly measure the mass exchange in this system. How? By looking at the orbit of the star. If the mass balance between the donor star and the neutron star changes over time, we expect the period of the system to decrease, okay? This is well known from accretion theory. You will think that this cannot be observable over short time scales, but actually, if you have super radiant accretion to this level, it is observable. You cannot measure directly the change of orbital period, but you can measure a shift of the orbital phases over time, a parabolic shift like this. So over the years, 7 years of observations, we've tracked the orbital phase of this pulsar, and we've used multi-parametric searches using different timing methods to constrain, because this source is also spinning up like crazy. So we need to measure the spin, the spin frequency, measure the spin up, and also measure the orbital phase. But thankfully, people in the radio and gamma ray domain have developed pretty precise timing methods that using the pulses can track all these parameters all together at the same time. And in particular, the method by Pletch and Clark used for Fermi pulsars is fantastic and permits to measure all these parameters together with high precision. And over the years, we tracked the orbital phase. And if we take the orbital phase, this was until 2016, we see that it was mostly compatible with a single period, no spin up. But then in 2020, we got another observation, and then another, and recently another one. I think it's pretty clear now that the orbital phase is coming much earlier than expected. So over time, the orbital period is decreasing, and this is absolutely not compatible with a single orbital period. But it's a very nice parabola. I'd say really, really nice, because the parabola describes the data even below their actual error bars. So I'm actually thinking that we are overestimating the error bars here. And this points to a mass transfer between the donor star and the pulsar of 10 to the minus 6 for 10 to the minus 6 solar masses per year, which is huge. It's about 200 times the Eddington limit in the standard sense. And this is actually a lower limit, because if you have any mass loss from the donor, this can mean a much higher limit as well, okay? So it's, I mean, it's pretty awesome to think about it. If it's true, of course. If it's true, you can directly use all the standard formulas and obtain with any one of the parameterization of the spin up, you can get like a dipolar field of 5×10 to the 13 Gauss, which is pretty high, not so extreme. It's not a magnetar, but it's a pretty high spin up. People have started questioning this thing, they say, oh, but in many low mass X-ray binaries in CBs, there is period jitter. So you observe a decay for a few years and then it starts expanding again, like this. I would like to point out that this is not a low mass system. So all the mechanisms that predict this period jitter cannot be applied to a high mass X-ray binary. There is another much more fundamental objection instead, which is that there are high mass X-ray binaries which have lower but kind of comparable as an order of magnitude orbital decays. And in that case, the luminosity is much, much lower. So if the same mechanism is at play, then you can have the observed orbital decay without being driven by the mass transfer, actually. Being driven, for example, by a change of the angular momentum of the donor star, because, for example, of synchronization or circularization of the orbit. In our case, it seems implausible. The eccentricity is very low, so the circularization should have been reached already. We find really no trace of eccentricity. We have a stringent upper limit on it. And seems weird not to have it circularized, but it's possible, okay? So this is, I think, the strongest objection that can be made besides theoretical ones based, oh, no, the timescales are wrong or other things. But I think this one is a very clear objection that we really need to work out. So there are many open questions that you can find here. If this is true, this accretion regime seems difficult to model. Okay, there are many evolutionary models that try to explain how ULXs are formed, and the time scales seem odd with this, but there are too many parameters in there. So we're working with theoreticians to try to understand what is this accretion regime. In any case, we've observed something, and I would really like to know which theoretical models can explain it, regardless of what I think, or regardless of what the current theoretical models think, because ULXs have disproved theoretical models for a long time now, and I think we're observing something new as something that needs to be investigated. I'll conclude first with a shout out to all the people creating open source software that we can use for our research, and then a small take-home message about what I've talked about, and I'll take any questions. Thank you.
Thank you, Matteo. Almost perfect timing. All right, are there questions for Matteo from the audience?
I ran a little late, sorry.
I need to check the Slack channel. One question there. No?
So in the HMXBs,
Closer to
does a trend change if you watch long enough? I'm just not familiar with the.
No, there is no trend change in HMXBs. They are almost perfect parabolas.
Okay, that's too bad.
I think the floor, Georgios.
Are there any other questions for Matteo? While we switch. If no, let's thank Matteo once again.
Sure. Yeah, no.
Okay. Next speaker, I'm sorry, I don't know your first name, Vasilopoulos?
Georgios.
Georgios. And he's going to talk about ULX pulsars hold the answer to beam or not to beam. And I'll tell you 3 minutes before the.
So, hi everyone. Thank you for being here, and thanks to our organizers for giving me the opportunity to speak about my favorite objects and the work that I have done with collaborators around the world. So, thanks to Tom and Matteo, you already know all the basic stuff. We're talking about off-nuclear bright sources in other galaxies and some of them in our own. And the idea is that these are actually the first objects that we have observed that we have concrete evidence that they are emitting above the Eddington limit for their masses. So if we see the Eddington limit for different masses, ULX pulsars are essentially standing just around there with normal neutron star masses, but with very high luminosities. And of course, there's the question like, maybe this has to do with the magnetic field, as Matteo mentioned, and some other ideas, maybe that this has to do with some beaming and super Eddington accretion. And they're all working together in these sources. So we're trying to explore this and try to find evidence that support either idea, disprove or prove their predictions. And I will mainly focus on the temporal properties of the sources. But first, a few more things. You've seen this plot before. The idea is that we have an accretion disk inside the spherization radius. We have some kind of beaming. The idea is that we have also outflows. This is speculated since the 70s, but there are even more recent and complicated models. But let's see, the idea is that we have some kind of beaming scale that scales with the mass. And if we focus on, instead of a black hole on a neutron star with a high magnetic field, then we add the magnetic field, the disk is sort of like pushed outwards. We have the magnetospheric radius, we have, let's say, outflows. And the basic question here is also, as Matteo mentioned, we have luminosity from the central source that we treat as a normal pulsar, maybe, but we also have the luminosity from the accretion disk. And maybe in some cases these are comparable, maybe in some cases the luminosity of the accreting pulsar dominates. So this is also something that we don't really know, and it's very difficult to model for the systems. And what about beaming? Let's talk a little bit about that. We have this sketch like for a ULX pulsar. We have pulsed emission from the central source, and this pulsed emission can, hit the walls of this funnel and then being reprocessed and re-emitted as non-pulsed emission. So that's what we observe, and it's very difficult to disentangle. Again, the idea is that what happens in black holes and super Eddington accretion must scale also, or should scale for high magnetized ULX pulsars. Now, there have been some recent models, and this is very interesting, that inside the magnetospheric radius, inside the spherization radius, of when the magnetospheric radius is lower, you have sort of to readjust all these standard models for the accretion, for the size of the magnetospheric radius. So in general, instead of having the typical relation where the magnetospheric radius scales with mass accretion rate, you have sort of like a flattening around the Eddington limit, where the magnetospheric radius becomes insensitive to mass accretion changes. And this is also something that has been shown by different authors in theoretical models, and we can use it as a first-order approximation in treatment of the accretion disk in these systems. So again, something that Matteo mentioned, we have like typical systems where we have changes between the accretor and the propeller regime. Basically, if the disk goes inside the corrotation radius or outside the corrotation radius, then we can have a transfer of mass onto the neutron star. We have spin-up systems or spin-down systems, and we have different torque models that describe that. And here on the right, you can see several of these models, and they're all basically similar. Like you can see some equilibrium point, and the main difference is that each model requires a different magnetic field for that equilibrium point. But like we can use them and get estimates for the magnetic field if a system is in equilibrium or in the slow rotational regime. So now we'll talk about some of the work we have done using these first principles and trying to find evidence in support of beaming or how the mass accretion affects the accretion disk. And yeah, so the first system is one of my favorites, is NGC300 ULX1 that Dom mentioned a few things. So I should just say a few things about that. This was also discovered in 2010 as a probably supernova system. And this was soon realized to be something like a supernova imposter because there was an optical counterpart after the explosion. There was a system there. So actually, it's very interesting that after the spike in 2010, the system luminosity decreases. And it became bright again in 2010, 2016, where you can see the star up in the right. And in these observations by NuSTAR and XMM, we found pulsations. And these are actually very different pulsations than typical ULX pulsars because they are very strong. Like the pulse fraction of this system was more than 70% in the hard band. The other interesting thing is that if we compare the soft data from XMM between 2010 and 2016, we find evidence that all the spectral variability is due to absorption. So there is an idea that maybe what's changing is not the mass accretion rate between 2010 and 16, but maybe we have some kind of obscuration. And the other interesting thing about the system is that looking at the NuSTAR data, there was evidence for a cyclotron line, and we have like an estimate for a magnetic field. Of course, it's still strange to know exactly where the cyclotron line, if it's real, where it is formed, like which height above the neutron star, but it still is a first order of magnitude estimation. So after the discovery of the system, and within 2018, we had like a long monitoring of the system with Swift, and basically the luminosity seemed, or the flux seemed to be stable, but then at the end of 2018, we saw this drop that lasted for a few months. And here was an ideal case to say, okay, we will follow the system, and if it becomes brighter again, we will know if it was obscuration that caused this dip or actual change in the mass accretion rate. And we followed it also with NiSER, and this is what we found. We found that it seems that the spin up continued at a constant rate. And just to zoom in those 2 points that you see on the left, you can see the last point before the gap, and you can see how we would expect the spin up to continue based on standard torque models if we follow the flux as a proxy of the mass accretion rate. And this is with a blue line. And it's very off. In reality, if we use a constant mass accretion rate for all this interval, we actually manage to follow up the spin evolution perfectly. And we get a magnetic field, which is basically in very good agreement with the cyclotron line. And this is very interesting too, that these two are in agreement. Now, again, you already saw that, so I'm not going to talk much about it. This is another system that we have seen that, and this is P13. And I was hoping to do the same in the future with NGC300 because we tried to follow it in the past few years, and we have never seen it bright again. So this smaller brightening that happened like 2 months after the deepening in 2018 was the only one. So we still don't know what's happening like all this time afterwards. Like, has the system turned off? Is it something that like an obscuration event that lasts many years? It's still like something that we debate and we don't know. So it's interesting to continue following the system and know what will happen in the future. And I will get back to that in a few slides. So the other system I would like to point out is M51 ULX7, which is another interesting system. And it was discovered by Rodriguez Castillo et al. And again, they did an amazing work analyzing the data from XMM, and they found like an orbital period of 2 days, a spin period of 2.8 seconds, and a very accurate, let's say, spin up of 10 to the minus 11 Hertz. Now, the interesting thing is that this system is about 2 times brighter than NGC300, but the spin-up period of the system is about 20 times slower. And what it means is that if we plot some torque models just to guide the eye, the NGC 300 is around the slow rotator regime, while M51 ULX7 is spinning very slowly, spinning up very slowly. So it should be in the propeller, not the propeller, the spin, close to spin equilibrium. And this gives a first estimate of the magnetic field based on that. But we still look evidence that can support that, like, are we close to equilibrium? Maybe we can see some propeller transitions or something else. So we looked at the Swift XRT monitoring data, and this is something that Murray did too. And we found a superorbital period of about 39 days, which seemed to be stable, although now there are new evidence, and you can ask Murray about that, that the superorbital period is changing with time. So it becomes a little larger within statistical uncertainties, but there are some evidence. There is also some evidence of some off points, like within that superorbital cycle, you can see some points with low flux, and maybe these are propeller transitions, but again, it's a question. And if we look at it and try to visualize it, basically the superorbital cycle on the system could translate to some precession on the accretion disk and the outflows that cause this change in observed flux. And that's also another idea that maybe this is happening in NGC 300 ULX1, but in a longer time scale. And the other thing is that NGC 300, we don't know the orbital period. And actually all the estimations point to an orbital period of more than 1 or 2 years. And maybe this has to do with scaling the precession periods, again, in time scales of larger than a year. So this happened also a few years back when I was at the Chandra workshop, and I was looking at Hannah's talk about ULX7, and I saw this archival data on Chandra. And Andres Grubiter at the time was also working in this data and had analyzed all of them for some spectral studies that that was mentioned before. So we tried to look at this data back from 2000, well, I can't remember the date exactly. And if we go back the superorbital period and we just extrapolate, it matches perfectly the Chandra data. So it seems that all this superorbital cycle was very clear, very stable for all these years, apart from that points on the right that might be evidence of propeller transition. Now, the other thing that we noticed looking at this data, maybe it's not visible immediately by eye, is that there are some dips in the data. And these dips are actually happening around the 2-day period, that it's the orbital period. And if we zoom a little bit further in the first 15 days, we can now clearly see that these dips, whenever Chandra was observing, we could see the dips. And we did the statistical tests, and we found that these dips are significant, found like with a above 3 sigma level. And this period of the dips actually matches exactly the orbital period. So this is actually the first ULX pulsar system that we find evidence of dips and in orbital timescales. And because we have all this information from X-ray Dopplers and the dips, we can sort of try to find some constraints on the system. The idea is that we have a binary separation that is about 2 times the donor star radius. So you can do some simple math and find that if we assume that the funnel of the outflows has the same, is in the orbit, or the same plane as the orbit period, the funnel should be about 120 degrees wide or 60 degrees half opening angle. And this actually gives you a very well constraint on the beaming, because it means that any beaming that's happening on the system should be less than a factor of 2 with these rough constraints. And this is actually very strange, because if we assume like the typical relations adopted by King et al., where the beaming scales with mass accretion rate, we would expect for this luminosity a much larger beaming factor. So it seems that on this system, it's not actually that, maybe this relation needs to be recalculated. And this is actually very interesting, another prospect, as Matteo mentioned for M82 X-2, that now that we have this object and we have observed these dips, we can actually follow up the dips evolution and find if the binary orbit changes with time. And this is something I would love to do in the future. Unfortunately, we tried to do it with Chandra, but we had some problems that Chandra cannot longer sustain that long observations more than 100 kiloseconds for this target, maybe to track the dips. So finally, this is something I added last night because I thought I would have time to talk about it, assuming that Dom and Matteo would give a perfect introduction for these objects. So this is an object. This is actually let's say a nearby ULX pulsar or a transient ULX pulsar. It's not the same as the typical pulsars, ULX pulsars that we see, but it's a system located in the Large Magellanic Cloud or between the Large and the Small Magellanic Cloud. So we know the distance is about 62 kiloparsecs. And in 2019, 2020, gave a super Eddington outburst that exceeded the Eddington limit for about 10 times the Eddington limit. And this was followed up with NiSTAR, with NuSTAR, and with NuSTAR with some amazing broadband spectra at around 3-4 times the Eddington limit, and with AstroSat and HMXBs. So what we first found out when we looked at this data was that from the pulse profile monitoring with NiSTAR, we could find that the pulse profile didn't change almost at all when the luminosity changed for a factor above the Eddington limit for a factor of 10, like between the Eddington limit and 2 times or 1 times 10 to the 39, the pulse profile remained constant. And this means that if we assume that we have some kind of funnel that evolves with mass accretion rate and the funnel becomes narrower and narrower, we would expect to see changes in the pulse profile, but we don't. The other interesting thing is something that we have now submitted and we hope to get a reply soon, but I would like to show it to you, is that when we look at the HMXBs data at the peak of the outburst, which was a little bit over 10 to the 39, we could see clear pulsations between 1 kV, which is the lower limit, up to about 100 kV, which is the sensitivity limit, let's say, for the source. And you can see actually on the left axis, you can see the number of counts, just to get an idea of the statistics. And on the right, you can see the normalization. So basically, above 1 point of 60 kV, we are dominated by background. But even if we go to 80 to 100 or 90 to 110 kV, we can see clear evidence of pulsations. So it's very interesting that we have a source that is emitting 10 times the Eddington limit, and we can see pulsations at these high energies. And yeah, I think I can have my conclusion slide, basically say that for NGC300, it was a perfect source where we can scale the mass accretion rate because of the high pulsations. We know that what we see as a flux or a luminosity is actually translates to the mass accretion rate, and we get a normal type magnetic field that agrees with the cyclotron line estimates. For M51 ULX7, again, we have evidence that the system is rotating near spin equilibrium. We see evidence of propeller transition in Swift, but mostly in Chandra data. And we have found, for the first time, discovery of periodic dips on orbital timescales that can be very useful in the future to track the orbital period evolution. And the main focus is that from all this, it seems that the standard recipe for beaming doesn't seem to work for these sources that are emitting like around 10 to 50 times the Eddington limit. It seems that beaming is much lower than the one it's predicted from the standard relation. And thank you for your time.
Thank you. We have questions. We have one question here.
Hi, Georges. Very nice talk. So I have a question about M51. So it wasn't clear to me, do you think the dips are caused by obscuration by the donor star or by the disk or funnel or whatever?
I think they happen from the donor star because they are strictly periodic, and the disk, we know that the disk has a superorbital period of 40 days. So I cannot think like, I think it's basically like Hercules X1 that you have a combination of superorbital modulation and obscuration from the donor star. Now, it's not completely eclipses, but it's more like that we see on the edge of the star. So it might be the outer atmosphere of the star, or it might be, an idea might be that it comes from strongly ionized wind from the star that causes some kind of dimming, because it's like only a few % of the flux.
But that should put some really nice limits on the donor star properties, actually. Because then you pretty much know the inclination. If you know the orbital period, you can get a sense of the mass.
Yeah, that's. I think we did some estimate on the mass and the radius, and combined with the orbital solution. So I think there's something between 8 and 10 masses, like solar masses, but have to check the number.
Okay, thanks.
I actually have a follow-up question on the, and probably very naive, but why is it so obvious to you that the change is due to obscuration and not due to an intrinsic change in the luminosity?
For M51 ULX setting?
Yes, yeah. I mean, I see a change in the continuum. Why is it so obvious there has to be obscuration?
You mean for the orbital dips or?
No. I don't know if we're talking about the same thing, but when you show the difference between 2010 and 2016, something like that.
This was based on X-ray spectral modeling.
Right.
And the X-ray spectra, you could fit them with the same model, the spectral model, letting only the partial absorption coverage to vary. And this was like an indication because spectral models for ULXs are not very well developed, I would say. So we didn't know. It was a first estimation. And then the proof, let's say, came from tracking the spin evolution during these dimming events, because if we had changes in the spectral shape or mass accretion rate, we would expect to have changes on the spin up of the object too.
I see.
On the spin up rate. Well, while it remained constant spin up rate for almost 4 years.
Okay.
Thanks.
I'm not sure we have any questions from Slack.
No, but I would be happy to answer in the breaks. Or
one more question here, and then we move on.
So please forgive me for the kind of dumb question, but isn't it like if you're saying there's beaming involved in ULXs, how do we even know that they're super Eddington accretion? Couldn't you get it? Something like they're just very bright because they're beamed, but they're not actually like having quite that high a total luminosity.
Yeah. So yeah, as I said, like for NGC 300, because we see pulsations at an 80% pulse fraction, we know that there shouldn't be any beaming involved. There was a recent work by Mustikov et al. That showed that if we have a funnel where you have scatter on the walls of the funnel, pulse fraction should decrease significantly. So we know that for the other system. For M51, it's more like a combination of different things that we sort of like try to constrain the spin up, not try to constrain what properties would give you a spin equilibrium. But we can discuss it later.
Thanks, George, one more time. Thank you. Now, the last but not least speaker of the session is Hannah Earnshaw, and their talk is about unusual spectral variability of NGC 4190 ULX X1. And I'll signal you 3 minutes before.
Great, thank you. All right. Hello, everyone. My name is Hannah Earnshaw. My pronouns are they, them. I'm a staff scientist in the NuSTAR group at Caltech. And I'm going to present today a bit of a case study on one particular ULX I'm looking at. I look at a bunch of ULXs. If you can't get enough of ULXs and want to read about more of them later, I have a paper up on the archive today, actually, about a completely different one in NGC 925, which is also doing some interesting things. But today I'll be talking about NGC 4190 ULX1. So first of all, thanks to Dom and the rest for basically ensuring that I don't have to do a very long introduction today. I just want to bring our attention back to, could you stop doing that soon, please? To the kind of usual form of a ULX spectrum that, if you have a good enough data quality, can be fitted with, say, 2 thermal components from, say, a super Eddington sort of slim disk, this kind of broadened thermal component, and then a cooler one, maybe due to an outflow or some kind of outer disk. And then this kind of high energy excess, which can be fitted with a power law, possibly due to some form of corona or an accretion column. And in persistent ULXs, we do see spectral variability of various different kinds. You have these ones here that were mentioned earlier, which have this kind of mysterious high energy kind of congruence where this is very consistent high energy emission and lots of variation then in the lower energy emission. We have others that seem to have more variability across the whole wavelength range, some that seem to vary more at high energy. So there's a range of different behaviors going on here. Another thing that I want to talk a bit about is also short-term variability. In ULXs, there's some interesting behavior that we want to look out for, not least being, of course, pulsations. That's the most interesting thing to a lot of people. We want more pulsating ULXs, so we're always on the lookout for more of them. But also, some ULXs will show kind of sort of red noise in the power spectrum, increasing to lower energies that we often see in kind of accretion processes. A small number also include QPOs. They're not incredibly well understood at the moment, so finding more QPOs in ULXs would be cool to continue to study them. So this short-term variability is actually part of the motivation for why we wanted to look at NGC 4190 ULX1, because NuSTAR is very good at doing timing stuff. It's got an excellent time resolution. And another mission that we can do cool timing stuff with is NISA. And ULXs aren't really something that we can study with NISA for the most part because they're extragalactic, because they have comparably low fluxes, and because they're often found in crowded sources, as maybe like an AGN in the center of the host galaxy, or there's other X-ray sources around. Usually they're not really suitable targets for NISA. But this one's quite cool. This one's in a very nearby galaxy, just under 3 megaparsecs away. It's a low surface brightness galaxy. It doesn't have any other X-ray sources in it, or at least no bright ones that can interfere. You can see this nice Chandra image with the nicer field of view. You can see this is just this nice little isolated source. For the longest time, we didn't actually follow this up because it's right near the center of the galaxy. And so it kind of went through all of our filters, kind of filtering out sources near the centers of galaxies because, you know, AGNs will get in the way. But we then came back and realized that actually, no, this is ideal for a nicer NuSTAR observation. It's also got a persistently high flux. I haven't actually put the luminosity on this plot, but there's goes from about 10 to the 39 x per second at the lowest flux that we've observed it at with Swift, up to about 10 to the 14. It spends most of its time in this kind of mid-range here. So yeah, so it was a good target for this joint observation. Also, we can see this kind of unusual property in the archival XMM data is that while we do expect a kind of this turnover at high energies in ULX spectra, what this usually requires NuSTAR to actually properly detect and confirm that this kind of turnover is here. Actually, this is quite a low energy break in the ULX spectrum for this source. We can see it quite clearly even just in the XMM spectra. So this is quite a good source to sort of investigate that break a little bit more. So we performed a joint NISA and NuSTAR observation back in 2020. It was persistently bright during that observation, kind of did a little bit of a decrease in flux towards the end. But yeah, and sort of part of the complication of doing this with NISA is that while it's a high flux source for a ULX, it is pretty comparable with the flux of the NISA background. So we basically have this kind of relatively narrow range in which the source is bright over the background for NISA, but that's enough for us to work with. And so I'm going to start off by looking at the variability, because this was the kind of the sort of driving motivation, at least for me, to use NiSTAR and NuSTAR to observe this source, and we found, well, actually, it's not as interesting as I kind of hoped. We don't see any significant QPOs, no strong evidence for coherent pulsations, but we do see this kind of red noise in the power spectra of both NiSTAR and NuSTAR, as is sometimes seen for ULXs, and this is kind of the kind of signature you expect from accreting sources. So that's very nice. We did search for pulsations, we did perform an accelerated pulsation search. Unfortunately, none were detected between 0.01 Hertz and 10 Hertz. Which is a bit of a shame, but because of just the sheer amount of data that we actually got from this source, we can put reasonably strong limits on the pulse fraction. So we can see that we can rule out the sort of NGC 300 ULX1 like kind of very strong pulsations from the get-go. But at the same time, these limits there, we have detected kind of pulse fractions below these limits from sources as well. So it's not a complete kind of ruling out of pulsations from this source, but certainly none detected. But that's okay, because actually some of the interesting stuff that this source is doing is more to do with its spectral variability over time. So let's look first at the broadband spectrum from this observation. So as I mentioned before, we can fit ULX spectra with two thermal component models plus a hard excess. So we see this, just this behavior in this source. If we fit this with a cool disk black body, a hot broadened disk representing an advection-dominated kind of super Eddington accretion disk, we find that we see that the very same kind of excess above 10 keV as we see in a lot of other ULXs. So that's pretty cool. However, if we actually then fit this hard excess, either with, say, a simple convolution model to represent some kind of corona possibly, or if we use a cutoff power law model to represent a potential accretion column. In both these cases, we find that actually the hot component, this component that's often broadened in ULX spectra, is actually not required to be broadened at all. So we find the kind of P kind of that defines the temperature profile of the disk is pretty close to, if not kind of a little narrower than you'd expect from your bog standard thin accretion disk without any broadening. So that's kind of interesting. We'll come back to why that might be later. And so yeah, this is just then showing that we can do this with simple a cutoff power law. Because we don't detect pulsations, we can't actually do a sort of pulse phase resolved spectroscopy, but I've just done what was sort of done with the kind of collection that Don Walton showed earlier, which is sort of taking the average sort of properties of cutoff power laws fitted to pulse phase resolved spectroscopy before, and just using that as a kind of an example shaped for a possible accretion column, and it can fit the spectrum quite nicely. Now what we can do after that is we can then go back to the archival XMM data, and while these aren't broadband spectra, we can still basically fit them with the same model of these two thermal components plus a simple or a cutoff power law model, and see what happens. So we froze the kind of the high energy model parameters and only allowed the normalization of the cutoff power law to vary, and took a look at what this did to our thermal components. And so we can put together a sort of luminosity temperature relation plot to try and see what's going on with these components. So first of all, we don't really get any great constraints on the cool component. That's fine. Let's just sit down here. doing what it's doing. The interesting part here is then looking at the behavior of the hot component. Now, we saw earlier that spectral wise, at least, we don't require a broadened disk to fit this component. However, when we look at the luminosity temperature relationship of this component, we see a relation that's consistent with the luminosity being proportional to the temperature squared, which is what you'd expect from an advection-dominated Super Eddington sinus slim disk, as opposed to what you'd expect from a sub-Eddington thin disk, which is more like T to the power of 4. As a bit of a sanity check, I also did this with just because we're sort of overfitting the XMM spectra for this. I also looked at what happens if we just fit the XMM spectra with a single kind of thermal model, and we get a very similar kind of relation. And this holds for kind of the various different combinations of models. I've used this one I'm showing is quite clear. It's just the disk BB plus disk PBB plus cutoff power law. This works also if we use a simple model or if we use just two disk BB components. But basically we see this, sort of slightly flatter than expected, more like an advection dominated disk component. The caveat here is obviously, we are kind of leaning on the XMM spectra for this. What would be ideal is we go and take some more broadband spectra of this source just to see if this relationship holds up. But for now, at least, it's an interesting clue that perhaps even if this component isn't required to be broadened in the spectral fit, we're still looking at Super Eddington accretion disk. So the implications of this, first off, if we did pretend that we were looking at just this normal kind of sub-Eddington thin disk, and we ran through the numbers and calculated what this would imply about the inner disk radius, and kind of work that math through, we can get a sort of predicted black hole mass of around 10 solar masses, which would then imply that the actual luminosity we see of this source is Super Eddington. So we can't get a self-consistent picture of this source if we assume that what we're seeing in the hot component is actually a sub-Eddington thin disk. So that, again, implies that what we are looking at is a Super Eddington advection-dominated disk, which is somehow has a narrower profile in the spectrum than expected. Now, what could be in play here is a truncated slim disk. So if this disk didn't go all the way to the innermost stable circular orbit, but instead was truncated by a strong magnetic field, then the kind of range of temperatures that we see from this disk would be smaller than what you'd expect for the full disk. So it would have a sort of a narrower profile in the spectrum. So this could indicate a source in which the magnetospheric radius is not as large as, but is kind of approaching the spherization radius. So we're only seeing kind of a bit of a narrow band of this Super Eddington disk. Obviously, we don't have pulsation detection to back up this source being a neutron star yet, but we have also established, sort of, and you've seen in previous talks, that just because you don't detect pulsations from a source doesn't mean it's not necessarily a neutron star. But then there's also this kind of complex behavior in which if we kind of go back and look at the XMM Newton spectra, if we wanted to fit this with a cutoff power law for an accretion column, you'd see that the normalization of that accretion column, so that the kind of flux that we get out of it would have to be lower for these slightly lower luminosity and kind of cooler temperature spectra. And so this maybe adds a little complexity to the picture, since while it would imply that that maybe there was sort of more truncation in those cases, it sort of implies lower flux from an accretion column. So maybe there's some kind of precession in play here that's potentially kind of obscuring the kind of innermost emission, these cases. So this is a bit of a work in progress. There's a few things going on, and most importantly, though, it's a very good source for future follow-up observations, looking again for evidence of pulsations and kind of pinning down what the spectral variability is doing. So yeah, that's it. Thank you.
Thank you, Hannah. We have time for 1 or 2 questions.
Hi, Anna. Great talk. The luminosity relation you were showing is just based off the XMM data, if I'm remembering that correctly?
The XMM data, and then also this single kind of broadband fit with a nicer NuSTAR.
Okay. So 2 questions. That's just because you have, how many XMM observations was there?
So three archival XMM observations. Yeah.
Are there plans to have another NuSTAR nicer observation?
I'm certainly going to make those plans. Yeah, I'm planning to propose for more time on this to add some more broadband spectra to this. So, you know, if you end up sitting on a TAC in the near future, bear it in mind.
I hope you get it. Great.
Thanks.
Thanks.
I'm not sure if we have any questions on Zoom. Is anybody checking that, Matteo? No questions on Zoom. Are there any other questions in the audience for Hannah?
I think everyone wants coffee.
Otherwise, we'll go to the coffee break. Let's thank Hannah one more time. Okay, let's continue with the last talk of this session of ULXs, Marianne Heida. She's going to talk about the environments of ULXs. Is the presentation?
I hope, yeah. Oh, yes.
Take it away, Marianne.
Okay. Thanks, Javier. So good morning, everyone. Welcome back after the coffee break, sort of. So this last talk is going on a slightly different track than the previous ULX talks, because I'm not actually an X-ray astronomer. I do optical and infrared observations. So I will not be talking about the details of the accretion process, but more about the environments of these systems. Okay, so especially at, I guess, a NuSTAR meeting, why would you even study ULXs in the optical and the near infrared? I guess the first reason is that we have pretty pictures. I do not only need to show spectra. This actually looks pretty, but you can get a lot of information about scales that are not really probed by the X-ray observations. So in this image, this is a composite image where the red glow thing is H-alpha emission imaged by the Subaru telescope, and blue and green here are broadband HST observations. This is Holmberg 2 X1, which has been mentioned a couple times before. And what you see is that, so this red glow shows that there's a large nebula, large ionized nebula. This part here is actually directly ionized by the ULX, which is sort of somewhere at this point here. We see a counterpart, so this white dot is the optical counterpart of the X-ray source itself. So in some cases, we can actually see the donor stars of these ULXs. And then there's a whole bunch of stars around here that tell you something about the environment, that can actually give you some information about the age of these systems and in what kind of places do you form these systems, which tells you something about the binary evolution pathways that actually form ultraluminous X-ray sources. So there's sort of 3 main things that we would like to learn from optical and infrared observations. So like I said, donor stars, what kind of donor stars are we looking at? There's these surrounding nebulae that can actually tell you something about, for example, the beaming. And then what are the ages mainly of the surrounding stellar populations, and in what kind of environments do you form these systems? So starting with donor stars, if we can observe donor stars directly, that can give us a lot of information about these systems. If we can take spectra, especially if we can take phase resolved spectra, that is necessary to eventually get to dynamical mass measurements for ULX accretors. And this is the only way to show that a ULX accretor is actually a black hole. So for the neutron stars, we can see the pulsations. We know that they're neutron stars, but ULXs with black hole accretors, if they exist, assuming they exist, if you want to prove that something is a black hole, you're going to need these dynamical mass measurements, and you're going to need to observe the donor stars. And then, of course, it can also give us a detailed characterization. What kind of stars are these? How big are they? Are they filling their Roche lobe? How are they transferring this huge amount of mass onto the compact object? And that gives you a lot of background on how to form these things and where they will evolve further. For example, will they eventually become binary compact objects that could merge and form a gravitational wave source, for example. Unfortunately, these observations are really difficult. They are at the moment only possible for supergiant donors, and this is of course due to the fact that all the ULXs we know are, or almost all the ULXs we know are extragalactic sources, which means their counterparts are dim, and you can only see them if they are intrinsically very luminous. So we've done this for a handful of sources. We haven't actually managed to get any dynamical masses yet. There is only one system where there is a claim of an orbital period from the optical observations. Most of the orbital periods that we actually know from the X-ray timing, which was surprising. So if you only do photometry, so you take pretty pictures, you can actually see lower mass donors as well, but there are some complications here. One of them is that we do expect a contribution to the optical light from the accretion disk as well, and it's very difficult to determine if you're looking at a blue star or an accretion disk. So if you don't have a spectrum, you usually can't tell the difference between those two. And even if you're only looking at images, you still need very high resolution and very deep images. So you usually need to go to either use HST or 8-meter class telescopes with adaptive optics. So these are fairly expensive observations to do. Okay, so if we're looking at nebulae, I don't know, did I put in that? Sorry. If we're looking at nebulae, there are several ULXs that have these huge ionized nebulae around them, and only a handful really have been studied in detail, but you can learn some very interesting things. So here on the right, that's Holmberg 9 X1. This is one of the more famous nebulae out there. It's hundreds of parsecs large, really can't miss it. And this is mainly photoionized. And this means that you can use this nebula to determine what the beaming factor is here on a larger scale. And consistently, so this has been done for a handful of other sources, and we consistently find low beaming factors as we do from the X-ray observations, so less than a factor of 10 or so. This mainly tells you something about the beaming of the soft X-rays, because that's mainly what's ionizing these nebulae. But it sort of fits in a general picture that we don't see very strong beaming. Then on the left here, this is NGC 7793 S26, technically not a ULX, but probably more like an SS433-like system that we see very edge on. But this nebula is shock ionized, and we see a few other sources like this. And these kind of systems you can use to constrain the mechanical output of these ULXs. And again, we consistently find that the mechanical output is actually similar or even larger than the radiative output. So these ULXs really are producing, well, a lot of power. So surrounding stellar populations, what can we do here? Again, if you look at the photometry of a bunch of stars, say near a ULX, so in this case, this is NGC 5408 X1. This is from a paper by Fabien Grisset from 2012. He's done the same exercise for a couple of other sources. So you look at the stars that are near to the ULX, you plot them on a color magnitude diagram, and then you fit stellar tracks, and you see what kind of age best fits this population. In this case, he finds that this population is pretty young. This is like 5 million years. And that is an indication that you're probably looking at something with a very massive donor. If you were to find a very old population, then all the massive stars are gone, and you therefore need to have a low mass donor. So this is actually a very good way, if you find ULXs in old stellar populations, to prove that there is a low mass donor to the ULX, because we usually cannot see those directly. And again, so this requires deep HST imaging. It has only been done, this exercise, for a handful of sources, but the HST archive actually now has a lot of observations, especially of nearby galaxies, that happen to cover ULXs as well. So it would be possible to do this exercise for a much larger sample. Okay, so like I said, nebulae and these surrounding stellar populations have only been studied for a handful of sources. And it would be really good and nice to expand these kind of studies to larger populations. And so as a first step, we've gone and taken optical spectra, long slit spectra of 37 ULXs that are relatively nearby with the double spectrograph on the 200-inch telescope at Palomar. And the aim here was sort of twofold. So we put this is a long slit spectrograph. So we put the slits over the location of the ULX itself, and we also covered the nearest H2 region. These are very nice and bright regions that have very bright emission lines, and you can use those emission lines to measure the local metallicity. So we wanted to both look for nebulae, just to see how many of these systems have ULX nebulae, and also to measure the local metallicity and see if there's any relation, for example, between the metallicity and X-ray properties, because it has been suggested in the past that there could be, if you form ULXs in low metallicity regions, there you could form more massive black holes, because massive stars lose less mass in winds, so they can implode to form more massive black holes, and therefore they could be brighter in X-rays. Whether this really holds in the face of this 10 to the 41 ergs per second neutron star, I don't know. But this has been suggested in the past, so we wanted to see, is there any relationship between the X-ray luminosity that we see and the metallicity? Okay, so you take a bunch of spectra, we reduce the data, we remove the stellar contribution, and then you're left with just the emission line spectrum. And the first thing you do then usually is plot these diagnostic diagrams. So here on the y-axis, these are simply emission line ratios, flux ratios of emission lines. So on the y-axis is an oxygen 3 forbidden line versus H beta. And then on the x-axis here is nitrogen over H alpha and sulfur over H alpha. These are sort of typical plots that you make. And then these lines divide these areas where sort of on the left, on the lower left, so under this solid line, you find photoionized, say H2 regions. And then here on the upper right, you find stuff like AGN, liners, stuff that is either X-ray ionized or shock ionized. It's actually really difficult to tell the difference between ionization by hard X-rays and by shocks. Okay, so what we see here is that I've plotted 3 different symbols. So in the green diamonds are H2 regions. So our normal H2 regions where the ULX is somewhere else. Then the blue circles are H2 regions where the ULX is located inside the H2 region. And the yellow stars are the ULX nebulae that we found. And what you see is that at least all the H2 regions are nicely where you expect them in the H2 region part of this plot, which is in a sense good because this means that we can indeed use the relationships that exist for H2 regions to calculate the metallicity. And we find some of the ULX nebulae actually in this upper right corner, which means that those are probably shock ionized nebulae. So those would be very interesting to follow up to see to calculate the mechanical output of these systems. Okay, so then we go on and actually compute the metallicities of these H2 regions, and we find a pretty wide spread. So here again are systems that are, let's see, ULXs with a ULX nebula, ULXs that are inside H2 regions, and ULXs that don't have a nebula. There's really no difference in the spread of metallicities that we find. So we don't really find any relationship between the metallicity and the kind of environment that these things are in. We do find a pretty wide spread, so from about 7.7 to 8.7 on this wonderful log O over H plus 12 scale. So solar metallicity here is about 8.6. So we do see that actually most of these are around solar, which makes sense because we're looking at nearby galaxies, nearby large galaxies that have more or less solar metallicity. But we do actually have a significant sample also, mainly ULXs in dwarf galaxies at lower metallicity. And here on the right, what I plotted is the metallicity that we measured versus the metallicity that we actually expect given the known relationship, the known gradient of metallicity in these host galaxies, at least for the galaxies that have a known metallicity gradient. And we see that actually it matches really well. So it looks like these ULXs are, they're not formed in special places in their galaxy. They just have, they're just formed somewhere with the local metallicity, except that at the highest metallicity end, we sort of see that consistently we find lower metallicities than you'd expect. And this is still a fairly small sample, so I'm not going to make any really strong claims about this, but it'd be really interesting to see if this holds up for a larger sample of sources, because that might indicate that indeed at, say, solar metallicity and above, you would form these ULXs maybe preferentially in slightly lower metallicity zones within their galaxy. Okay, so then we plotted this against X-ray properties. On the left here is the peak X-ray luminosity that's known for these systems, and on the right are hardness ratios. And here we really don't see any relation. There is no indication whatsoever that you find higher X-ray luminosities for lower metallicities. And this is still a fairly small sample, so it'd be nice to, again, to follow this up for a larger sample of sources. But there doesn't, at least this doesn't point to forming like really massive black holes that reach very high X-ray luminosities. Okay, so then we looked at ULX nebulae as well, and we find nebular emission around about a third of the ULXs in our sample, 11 in total. 5 of those haven't been reported before, so these are definitely interesting for follow-up observations. These are not all necessarily these really large nebula that we find in other sources like Homburg 9. This is probably also why they haven't been found before, because the really big ones are pretty obvious. But if you have a smaller nebula, it's easier to miss in H alpha observations. So this is something that is interesting for follow-up observations. Then we find another 1/3 of our sources are located inside larger H2 regions, and the rest of them really don't show any emission lines. So I think there's really work to do here to figure out why some of these sources show nebulae and why others don't. My best guess, it might have something to do with the ages of these systems, but this is really something that requires some follow-up work. Okay, so to conclude, optical and infrared observations are really, really useful if you want to learn about the larger scales of ULXs and where they fit in the whole story of binary evolution. And to look at the environment of ULXs, we've started to go towards a larger sample. We took spectra of 37 ULXs, measured local metallicities, and looked for nebular emission. And the next step will be to actually get the ages of surrounding populations. All these systems have existing HST observations, and we will use the metallicities that we measured to actually constrain the ages that you can get from that. But that is future work. Okay, and I will just leave the slide up. If anybody would like to visit ESO at some point in Garching, there are tons of opportunities. And if you're interested, please come talk to me or George, who is somewhere in the audience there. Thank you.
Okay, thank you, Marianne. Do we have questions for Marianne today? Everything was extremely clear.
Without the imaging, how do you know the nebula are actually associated with the ULX as opposed to some other?
So, I mean, imaging exists of these regions. So we know where the ULX is. So we know where we put the slit. But yeah, follow-up imaging is definitely interesting because from our observations, we cannot really tell how big these nebulae are because you only have a small slit. So there's definitely a lot of follow-up work to be done there. There's also so Andres Gurpida has been doing some very interesting stuff with IFU observations of nebulae, and this is, some other people have done this in the past as well. But that's really, I think, a way forward because he can actually, I think for NGC 1313X something, can see that the sort of the larger nebula is photoionized, but then in the center you actually see shock ionization. there's some pretty cool stuff you can do.
So I have a question. When you talk about metallicity, you really what you're showing is oxygen, right? Have you looked into heavier metals, because that might give you more of a.
There is no easy way to do that.
No.
No. I mean, you can sometimes get iron as well, but the oxygen lines are really strong, so you can do this with relatively little observing time. So oxygen is what we get.
I see. I think we have one question on Slack. It says, maybe I missed this point from Marianne's talk. Did you detect nebulae mostly from brighter ULXs?
I did look at that. I don't think we see any relation there either.
Can you put your conclusions again? Sorry.
Yeah, it's not in the conclusions. But yeah, I tried splitting them up, but we don't really see any difference there.
All right, so we're going to have a little bit of a change of pace. We're going to move from the extragalactic to the galactic. Going to have so many more photons. And to kick us off, we have Earnshaw with an overview of galactic binaries and CVs.
Thanks. I'd just like to point out that CVs are also galactic binaries. So I don't know who put me down in the program as galactic binaries and CVs, but I find that offensive. Not really. Yeah, so I've been given the unenviable task of picking out highlights from the NuSTAR Galactic Binaries working group in just a matter of 20-25 minutes. And it's unenviable not because there aren't any results, it's because there's too many results to talk about. But here we go. Thanks to the organizers for inviting me to give this talk. Originally, John Tomsic was supposed to give this talk, but he can't make it because something to do with a telescope that he's been given to work on COSI, I don't know. Anyway, so let's just have a quick outline of what I'm going to talk about. The first part is kind of like who we are, what we do, and I'll just drop in some publication statistics and the sorts of topics that we talk about. Then I'll dive into some research highlights from our group, and I've tried to break it down into, I guess, 4 key topics. That will be black hole reflection, neutron stars in high mass X-ray binaries, magnetic CVs, and one of the funnest kind of quirks of NuSTAR is the ability to point at or near the sun, and I want to talk a little bit about that as well. So we have telecons every 2 weeks. This is the list of people the email goes out to. I've highlighted in bold some of the people I know are giving talks or posters here. And I just want to point out that the stuff I'm going to talk about today is just an overview. So I can't get into too much detail because I do not have the time or the knowledge, to be honest, beyond what these people have. So go seek these people out and talk to them and see their talks and see their posters, because they will have much more information than me. So some statistics. Last time NuSTAR had a science meeting was November 2016 at Caltech. And since then, the Galactic Binaries Working Group has produced 43 journal papers, 8 PhD theses, the authors of which are named there. And also, you know, just the small matter of Hans Bethe Prize, Kavli Prize, Head Dissertation Prize, one Head Mid-Career Prize, one Laboratory Astrophysics Division Early Career Award, and more recently a Pierce Prize. So, you know, pretty good group of people. And that's like since 2016. I haven't even mentioned Fiona's Rossi Prize from 2015. So let's break those publications down by year. Since November 2016 again, we're seeing around 8-9 publications a year. If you consider it takes around a year-ish to write and publish a paper, you can see the effect of COVID in the 2021 statistics there. But we're still putting out quite a lot, even with the pandemic. And I like to think we do kind of a diverse array of topics. I mean, for a group that's called Galactic Binaries Working Group, it's as diverse as you could possibly be. Of those 43 papers, 23, about half of them have been on accreting black holes. And then the rest you can split up into neutron stars and a couple papers on magnetic CVs. And these are the kinds of things I'm going to highlight in the next few slides. 18 individual sources and one 19 source legacy survey have come out of those 43 publications. So let's talk about some actual highlights. In this section of the talk, I want to kind of focus on some key highlights that utilize the unique capabilities of NuSTAR itself. So that will be the energy range, the 3 to 78 keV energy range, and you know, the high energy resolution at those high energies, and of course the ability to point at or close to the sun. Those are the kind of criteria where I selected the highlights. So the first one is reflection spectroscopy, and Javier is staring at me here, so hopefully I do not screw this up. But basically the energy range of NuSTAR, the 3 to 78 keV range, gives us access to the reflection spectrum in X-ray binaries. And this is important, particularly in black holes, where if you model the reflection spectrum, you can help determine the spin of the black hole. And this figure kind of explains it quite nicely. You have in the top left, a artist's impression of a non-rotating black hole. And on the bottom left, we have a maximally rotating Kerr black hole. And on the right, you can see the kind of corresponding X-ray spectra that those are expected to produce. And what happens is, as the black hole rotates quicker, the ISCO, the innermost stable circular orbit, it gets closer to the black hole. And this has the effect of kind of smearing out the red portion of the ion line here. In the bottom right, you can see for the maximally rotating black hole, you get a much more smeared out ion line. And if you model that spectrum, you can then determine the inner disk radius, and that gives you the spin, essentially. And it all sounds very easy, but Javier's giving a talk tomorrow, and it probably isn't as easy as that sounds. Why do we care about spin? Well, first off, you're probing, you know, strong gravity within the innermost regions of the disk, i.e. at the ISCO. But other important things might be, for example, how are spin and jets related? We don't know if there is some correlation between jet power and spin. Sometimes you see some correlation, then the next paper you read, there is no correlation. So I think it's important to study spin of the black hole in the context of jet power and jet launching. The other interesting thing is that it could be some kind of probe of black hole formation or evolution. So gravitational wave black holes, LIGO Virgo black hole spins are often seem to be pretty low. This might point to some different evolutionary path compared to the ones we see in HMXBs. I'll show a slide later that shows that NuSTAR is kind of preferentially detecting high spins in black holes. And could this be an evolutionary effect? So I'll just show 4 results out of a million. Again, I'm sort of focusing on the last results since the last NuSTAR science meeting. Top left, we have a reflection spectrum of GX339, one of the most famous black hole X-ray binaries. And this is from Javier's paper in 2019, where they detected reflection in a so-called failed outburst. Okay, so normally GX339 has these long, really long outbursts. Sometimes they last like a year. This one didn't last a year, but they still detected reflection in this failed outburst and found that the inner disk was still pretty close to the black hole at that time. On the bottom left, we have a result from Yanjun, who measured reflection in Maxi J1631. And what we're actually watching here is the evolution of the ion line. So from top to bottom in that spectrum, what you're seeing is the ion line kind of shrinking, and you're seeing the disk truncating. If you compare and contrast that with the one on the top right of Maxi J1820, the reflection spectrum was actually pretty stable there. It didn't change too much. And so what Douglas detected there was a pretty stable reflection spectrum, but what was unstable were the timing properties. Those were the things that changed on rapid time scales. And what that told us was the temporal properties were something to do with the corona rather than the disk itself, because the reflection spectrum wasn't changing as rapidly. And then on the bottom right is just one plot from Riley's 2021 paper where they tested a couple of different families of reflection models, one of which shown here is the returning radiation model, where light is bent back from, the black hole bends light back and actually illuminates the disk. And they found that Boyu 1630 was consistent with this returning radiation model. And all of these are, I've just like given the Cliff Notes version here. There are at least 3 talks that might discuss some of these results later on in this conference. Here's our current status. I think it's ever so slightly out of date. I think there's slightly more than 27 spins measured now, maybe one more. This plot here shows in blue the NuSTAR measured spin measurements, and then also in the black points, those are the thermal continuum method of measuring spin. But you need to know like things that are actually quite hard to know when you to do the thermal method. So you need things like inclination, and you need the distance to the black hole to get good measurements from the thermal method. But they're mostly consistent except for a couple. I won't get into why. But as you can see, the blue points from NuSTAR, they're picking out kind of rapidly rotating black holes. Why is this? I mentioned it could be some evolutionary effect. Maybe accretion is spinning up the black hole rather than those LIGO-Virgo ones, which are just low spin mostly. I will leave that there for maybe for Javier to elaborate on, maybe. The next results I want to talk about are from high mass X-ray binaries, specifically ones containing neutron stars, so X-ray pulsars mostly. These are usually wind-fed, sometimes Roche lobe overflow systems, and they're important because what we're studying here is the physics of accretion in the high magnetic field regime. And what we can look at using NuSTAR are the cyclotron lines, which gives us access to constraining the magnetic field strength. And we can also study things like the energy dependence of pulsations in X-ray pulsars. And this gives us a way of measuring or constraining disk and X-ray pulse beam geometry. So I'll talk about just 2 results there. Cyclotron lines we've already heard about a little bit this morning. They allow us to estimate the B field, the magnetic field strength close to the neutron star surface, or you assume using the 12B12 rule. If you measure the line energy over kind of if you do phase resolved spectroscopy, you might be able to also probe the geometry of the magnetic field. But recent results have shown us that the cyclotron line energy can vary with luminosity. And this is a little puzzling because you don't expect the magnetic field strength to change on the timescales that the luminosity changes. Maybe it's something to do with you're not actually measuring it at the surface, you're measuring it at some distance above the surface. And that changes with luminosity. This all kind of came to a head with Felix's work on GX301-2, which shows 2 not harmonically related cyclotron features, which is even more puzzling. And what they came to the conclusion, they came to the conclusion that what they were actually measuring was, yes, 2 different cyclotron features that come from 2 different heights above the neutron star. And you can see from these plots here that NuSTAR is the only instrument that can do this in detail, because these cyclotron lines are at 50 keV, 30 keV. Another result from high mass X-ray binaries, neutron star, X-ray pulsars, etc. This comes from McKinley's work last year, where she measured, she did XMM plus NuSTAR, measuring LMCX4 and SMCX1. And what we see here is we see the NuSTAR data in blue, which is completely out of phase with XMM until the 3rd observation where it's not. And what we're seeing here is the precession of the disk. And so the hard X-rays, they come from the beam, the neutron star beam, and they get reprocessed by soft X-ray, reprocessed into soft X-rays, sorry, by the disk. And if you have a warp, then the reprocessed emission is out of phase. And if you measure that superorbital phase, superorbital modulation, you can constrain the beam and disk geometry. So if you check out McKinley's paper from last year, they've got some really, really beautiful plots showing how they've managed to constrain the disk geometry. And it's really fascinating. Again, I can't get into too much detail because I just don't have time. This is my bread and butter. I had to slip this in somehow because it's mine. So NuSTAR is actually really good at studying intermediate polars. What is an intermediate polar or magnetic cataclysmic variable? This artist's impression shows a white dwarf, which is accreting matter from a sun-like main sequence star. The magnetic field of the white dwarf, sorry, I've been talking too much about neutron stars. The magnetic field of the white dwarf kind of is high enough to disrupt the innermost regions of the accretion disk, and you get the matter falling along the magnetic field lines onto the magnetic poles of the white dwarf. Similar to some of the images that Dom showed in his talk as well, actually. And you get an accretion column when the matter reaches the surface of the white dwarf, it shocks, and the temperature of that shock is directly related to the velocity at which it falls from the inner disk onto the surface of the white dwarf. And because it's free fall, essentially, that's just related to the mass, gravity. So you can see from those equations there that if you can measure the shock temperature of this, well, if you can measure the temperature of this shock, then you should be able to have a handle on the mass. And the trouble is here, these shock temperatures are well above 10 keV, so you need your hard X-ray telescopes. And this is where NuSTAR comes in. We performed a legacy survey of around 1920 magnetic cataclysmic variables. It's the first one ever with a imaging hard X-ray telescope, and imaging is important here because you need to accurately constrain the background to accurately constrain the temperature because it's so high. This is our plot showing the mass distribution, and we find around 0.77 solar masses to be the average mass of a white dwarf in a magnetic cataclysmic variable. That's about the same as non-magnetic CVs. And so basically what we concluded was that accreting white dwarfs, whether they're magnetic or non-magnetic, doesn't matter, they are seemingly more massive than the non-accreting counterparts. So your isolated white dwarfs or your post-common envelope binaries, for example. The reasoning behind this is not totally clear. There's a couple of competing theories. One is that maybe angular momentum losses in the low mass white dwarf main sequence pairs means that they are actually unstable and cannot turn on as CVs. Or the other question is, maybe we don't understand the nova accretion cycles as much as we thought we did, and perhaps we can actually gain mass through accretion. It's an important question to answer. I do not have the answer to it just yet. But where do we go from here? Well, let's try and fill out some of the extremes of this distribution. Is there a population, for example, of high mass white dwarfs in intermediate polars? And this is where, again, NuSTAR can help. John Tomczyk and others are leading a program where they are constraining the nature of integral discovered hard X-ray sources. And a lot of these turn out to be intermediate polars. And so what he does is he uses Chandra to localize and then uses NuSTAR and XMM to get the spectrum, measure the mass. And the idea here is that if they're being discovered by integral, which is a very hard X-ray / gamma ray telescope, then they naturally have a pretty high temperature and therefore maybe a high mass. And so here's a couple of sources. On the top left, we have J18007, where we measured the mass to be 1.1 solar masses, still pretty high. Top right, J14091, which is approaching the Chandrasekhar mass limit. And then on the bottom there, we have J15038, which is again around 1.3 solar masses according to these models. Check out Ben's poster, which is over there, who will have a lot more information than me. Finally, and I think this is one of the coolest aspects of NuSTAR, is you can point it at the sun or near the sun. And so Sean Pike, who also has a talk later this week, came up with this program to constrain the nature, or well, just to be able to look at sun-constrained X-ray transients. So this is a figure from Sean's proposal last year. And what it's showing is the maxi discovered transients and their angular separation from the sun. And in the red band, those are the regions that no other X-ray telescope can access. It's sun constrained, except NuSTAR. Okay, so look at all those sources and we're seeing a lot, we're missing a lot, okay, that NuSTAR can access. So here's the idea. Maxi error circle is quite large, but Sean figured out this tiling program where you can tile and cover the majority of the maxi error circle. And if the source turns out to not quite be in those 4 tiles, you can still constrain where it is from ghost rays. That's the idea. However, he didn't have to do that, because in this one on the right, the real data, they found the source in the NuSTAR data. And what happened here, this is from Maxi J1848, from a paper that Sean put out this year, where it was discovered in December 2020, not accessible to Swift or any of those other telescopes, but it was accessible to NuSTAR. They constrained the location of it, and then around February of 2021, other telescopes could finally access it and localize it more, and they found it to be a brand new X-ray transient in the cluster Glimpse C01. And this is the data that Sean got from those pointings with NuSTAR. And you can see this, these 2 spectra are separated by only a week. And what we see is a state transition, right? So in the blue, we've got a very soft X-ray spectrum. And in the orange, we've got a power law dominated hard X-ray spectrum. And the point here is, if it wasn't for NuSTAR, we'd have missed all the fun stuff, right? So we're seeing state transitions, we're seeing reflection. And from that plot I showed a couple slides ago, there are in the last 10 years, there were 39 X-ray transients that were sun constrained to other telescopes. And NuSTAR can access that region. That's 4 a year, right? Who knows what we've missed? We can see that in the case of Maxi J1848, we would have missed the state transition, we would have missed measuring the spin if it is a black hole, and that kind of thing. So I'm really looking forward to seeing what Sean's proposal brings out. I am running out of time and I don't have enough time to go into everything. So here are some relevant talks and posters that you should all go and see. Although I have written on the bottom that you should just check out every single talk and poster, because there's just some really great stuff going on using NuSTAR. I haven't been able to talk about using reflection in neutron stars to measure the neutron star radius, or at least constrain the neutron star radius. I haven't gone into nearly enough detail on any of the stuff that I've talked about. Amruta's talk on millisecond pulsar timing, I haven't even begun to discuss that. So please go and check out all the talks and posters. As I said, this is a Cliff Notes version, but I will end with this conclusion slide. I think we're great. I think the NuSTAR Galactic Binaries Working Group has been brilliant. Highlight reel I've used in this slide. It's a highlight reel of binary astrophysics since its inception. 43 papers since our last meeting, and we're taking advantage of the unique capabilities of NuSTAR. I've highlighted some key results, and at the end there, I know it's a bit cliche, but bring on the next 10 years. I can't wait to see what happens in the next decade. So thank you very much, and pour one out for our glorious leader. I wish he was here, but thank you very much.
Thanks, Aaron. Do we have any questions?
Hi, you mentioned about the estimation of the masses of the white dwarf in IPs. How reliable are those measurements depending on what model you use for fitting the...
It's a great question. So the question was, how reliable are the measurements? So when you compare the X-ray measured masses to, let's say, the few that have optically determined masses, those are the ones where you have the inclination well enough constrained, they match up pretty well. However, there are some caveats. We still don't quite, I don't think anyway, there might be people who can comment on this. We still don't quite have a good enough handle on measuring the reflection in these white dwarf systems, because you get reflection from the surface of the white dwarf. And it's kind of an argument of how we treat that, of whether we're under or overestimating our masses. But so far, the optical masses versus the X-ray masses, so far they match up pretty well. That's a great question, thank you.
I have a potentially related question from the Slack from Kaya Mori. Have you considered the effect of the possibly unknown magnetosphere radius for determining intermediate polars white dwarf masses?
Yes, I have. I'm glad I'm getting questions about the polar stuff, because that's the stuff I can actually answer. Yes, so there is some debate as to whether the inner disk radius is exactly at the magnetospheric radius, or maybe it's a little bit closer, or the magnetospheric radius is not. We usually consider it to be infinite because it's far enough away that it can be considered infinite. Sometimes it can be a little closer, and that affects how fast it falls onto the white dwarf, and therefore the temperature. And yes, in the 2020 legacy survey paper, we do consider that effect, and we do that by measuring a break in the power spectrum, and that break in the power spectrum is supposed to be related to where that inner disk radius is. And yeah, that's where. But the conclusion still stands, even if we haven't considered that, because you can only ever underestimate the masses. And our main conclusion, if you don't take that into account, you can only ever underestimate the masses. But the conclusion is that white dwarf masses are more massive in accreting white dwarfs than they are in non-accreting white dwarfs. So that conclusion still holds.
Great. Is that one more question? An announcement. Okay. Any further questions? If not, let's thank Aaron again and go on to the announcement.
Thank you.
So this is lightning talks again. I'm missing a slide from Drabotka, Muhidin, and Mabizadeh. So if you can get me your slides somehow, that would be appreciated. Thank you.
All right. And coming up next, we have Nazma Islam talking about superorbital modulations of supergiant high mass X-ray binaries.
Hello, everyone. First of all, thanks to the organizers for organizing this conference and giving me the opportunity to talk about the work that I've been doing on trying to understand the superorbital modulation in supergiant high mass X-ray binaries. This work is in collaboration with Robin Corbett, who has really discovered 5 out of the 6 sources which show the superorbital modulations in supergiant high mass X-ray binaries. Joel Coley, Katya Poshmith, who is also here in the audience, and Felix Fürst. So what are superorbital modulation? So for many of the neutron star high mass X-ray binary, neutron star X-ray binary systems, we see a periodicity which is the spin period, and a periodicity which is the orbital period of the system. In addition to the spin and orbital period, you see a third type of periodicity, which is often greater than the orbital period of the system. And this is what we call as the superorbital modulations. For systems like Hercules X1, which is a Roche-Low overflow system, and we know that there's an accretion disk present in the system, the superorbital modulation is what is thought which happens because of the precision of this accretion disk. So in the schematic diagram, you see the source is periodically occulted along the line of sight by this precessing accretion disk, which gives rise to this on and off state in Hercules X1. For B high mass X-ray binaries, so these system, the companion star has a circumstellar decretion disk, And the neutron star periodically passes through this disk. And what we see, the superorbital modulation in these systems are related to the formation and depletion of this circumstellar accretion disk. We also see superorbital modulation in many pulsating ULXs. So this is a plot from Townsend and Charles, and the black points are the red points are the ULXs and the estimated superorbital period plotted against this orbital period. And they found that there is a correlation between the superorbital period and the orbital period of the system, which is similar to what you see for B HMXB system in our galaxy, which leads us to believe that maybe it's the similar mechanism which causes us to see superorbital variability in B HMXBs. There are similar mechanisms in play for the ULXs. So in the plot below, the area that I've highlighted, that is where the supergiant high mass X-ray binaries whose superorbital modulations have been discovered, they lie. So as you see, it's not a very as strong relation as to the BHMXBs, but it's lower. So what are supergiant high mass X-ray binaries? So these are a system mostly consisting of a neutron star, which have a companion star, which is either a late type O star or a B star as a donor star. And we consider them to be wind-fed binaries. The accretion that happens is from the stellar wind of the companion, the massive companion star. What we have discovered is you see superorbital modulation in 6 of these supergiant high mass X-ray binaries. Now, this is a very puzzling behavior because so far we know that there needs to be a stable disk, either a circumstellar disk or an accretion disk present for us to see a superorbital variability in the systems. Stellar winds, on the other hand, provides less structured environment compared to an accretion or a circumstellar disk. So this is the list of supergiant high mass X-ray binaries, its orbital period and superorbital period, and the spectral type of the donor star. So as you can see, the spectral type is very similar, a late type O or a B star, which leads us to first believe that maybe the answer lies in the wind of the stellars of the supergiant companion stars. So in this talk, I'll be presenting results from the 3 sources that I've highlighted here, but I'll be also comparing them with what we know for the other sources. Out of these sources, we have the classical supergiant systems like 4U1909 or 4U1538, but we also have SFXTs. So SFXTs are the systems which they are called super fast X-ray transients, a supergiant fast X-ray transient, sorry. And they have this very short flare, which is attributed to a very clumpy stellar wind in the system. The other thing to note here is the detection of superorbital modulation in 5 of the systems was found with swift bad light curves. And in 4 of them, it has been also discovered in the integral light curves, but only for 1, which is 0114, we have detected the superorbital modulations with the RXT-ASM light curves, which tends us to believe that the modulation that we are seeing is harder in nature. So this is the power spectra of using the 17 years of swift bad light curves for 3 of the sources. So in the top panel, you see the power spectra for 4U1909, and the very strong peak at 4.4 day is its orbital period. After that, you see 2 prominent peaks at 15.2 and its second harmonic 15.2 by 2, 7.5 days. And this is way above the white noise that is for these systems. So the white noise is the probability that the statistical noise in the system could mimic a peak at a certain significance level. So these peaks are way above what we can consider might occur from a statistical noise. So these are the peaks which we attribute to the superorbital modulation in the system. For the other 2 sources, 16418 and 16479, These two sources have X-ray eclipse in the system, which gives to very strong modulation peaks in the power spectra. So what we did is we removed the X-ray eclipses, and then we looked at the power spectra. So the orbital modulation is suppressed, and what we can see more clearly is the superorbital modulations in the system. And even here, in the, for 16418, we see both the fundamental and the second harmonic peaks, which are very strong. For 16479, the fundamental is strong, but the harmonic is at the level of 99.9% of its white noise. To look at these as a function of time, what we did is we constructed the fundamental, the dynamic power spectra, where we looked at these, the strength of the superorbital modulation as a function of its time. So the panel A is what we call the dynamic power spectra, and panel B is the ratio of the fundamental or the second harmonic to the mean power or the average power in the power spectrum. And as you can see, that at various times, the fundamental and the harmonic have are either present or have weakened and is consistent with the average power of the spectrum. So, which means that this particular phenomena of superorbital modulations that you see in supergiant high mass X-ray binaries are transient in nature or are present at different time scales of the order of years. So now you see them, and sometimes you don't. So these are for the other two sources, which also show a strong fundamental peak in its superorbital modulation, but at different times you also see the harmonic present. And the left one is for 16479, which is an SFXT, and for the right one is for 1538, which is a bright supergiant high mass X-ray binary. At various times, so in these systems, you see both the fundamental and the harmonic present in the dynamic power spectra. But that is not always the case. For 16493, we only see this, the fundamental present in the dynamic power spectra. And for 0114, this plot, if you flip it, it looks similar to the plot on the left. We only see the fundamental present. And for 0114, the superorbital modulations are always present. They don't disappear. So now the question arises is, why do we see very few of the supergiant high mass X-ray binaries with superorbital modulations? One reason could be that because the nature of these modulations are transient or happens over time scale of years, it could be possible that we are missing it out when we are looking at the long-term average power spectrum. So for example, for 16393, we looked at its the power spectrum, which is on the left panel, and we see the superorbital modulations are detected at a very low significance. But if you look at its dynamic power spectra, you see at certain times, the superorbital modulation at its fundamental are strongly present while it disappears at later time scales. So this could be the reason why the superorbital modulations are detected in supergiant high mass X-ray binaries. And we do believe that a more sensitive detection of power spectra might lead to more number of sources in which we could see the superorbital modulations. So now looking at the superorbital intensity profile, if I fold the entire SWIFT light curves with its superorbital period, for 16418, what I see is a double peaked behavior in its superorbital intensity profile. But if I take segments of time when a certain, either the fundamental or the second harmonic or both are present or absent in the dynamic power spectra, I see a completely different behavior of the superorbital intensity profiles. So for the time where both the fundamental and the harmonic is present, what I see is a broad peaked superorbital intensity profile for 16418. For time scales, when I see only the fundamental and the harmonic has weakened, the superorbital profile changes to a single peak structure. For the time period when both the fundamental and the harmonic are weak or are not apparent in the dynamic power spectra, the superorbital modulations are very less modulated, or there are no modulations seen in this light curves. And for the time when we only see the harmonic, we see a double peak power superorbital intensity profile. A similar behavior is also seen for 4U1909. So for the entire data, we see a single peak superorbital profile. But at different time segments, when both the fundamental and the second harmonic is present, you see a double peak structure. And when the fundamental is present, it changes to only a single peak structure. For 4U1538, the plot on the right panel shows the frequency, the spin period history of this source with Fermi GBM. And what we see is it had an episode of, so it went into a spin uptrend. And around the time, which is given by the first green line, what we see is the spin uptrend has changed and it had stopped. And then when the modulations came back, the spin uptrend again continued, which lead us to think that maybe the spin period is related to the spin period history of the sources showing superorbital modulation are related to the superorbital, the strength of the superorbital modulation in these systems. However, if for 4U1538, it is a bright source which has been modeled, which has been monitored extensively with SwiftBat and Fermi. For 4U1909 and 16418, the other two pulsars in the system, it is very difficult to make any strong conclusions from that because they have been sparsely monitored using different pointed observations. So the data is too sparse to conclude if the spin period evolution is tied to the superorbital modulation. So we recently proposed and got accepted an AstroSat proposal, which will regularly monitor the sources for its spin period. And with SwiftBat, we have the information of how the superorbital modulations look. And that would be crucial to see if the spin period evolution is tied to its superorbital modulation history. We also have NuSTAR observation, which we had triggered when the predicted superorbital maxima and minima of a cycle of the sources was thought. So that is given by the red lines at the top. Unfortunately, what we see is when the NuSTAR observations were carried out, both the superorbital modulation at its fundamental and harmonic had disappeared, which happened for 3 of the 6 sources. So that made us go back and come up with better strategies to target, to propose for observation to target when the superorbital modulations were there. But unfortunately, during this time, both the fundamental and the harmonic modulations had disappeared for all the 3 sources. So this is the NuSTAR light curve of 1909, which has been with its spin period of 603 seconds. And except the flare that you see in the superorbital maximum, the flux level of the superorbital minimum and the maximum, the predicted minimum and maximum is the same, and we do not see any change in the spectral parameters. This is also true for 16418. This is a candidate supergiant fast X-ray transient. And in this light curve, you can see the short flaring nature of the system in its with its observation with NuSTAR. And for 16479, which is an SFXT, which we consider, so there in the NuSTAR observation, we see the presence of two big flares. And we consider them, and they are thought to be the orbital phase locked X-ray flares, which are thought to be present in the system. So what could be the possible causes of the superorbital modulation? So it could be the tidal oscillations which happen when two non-synchronously rotating stars. So the star can modulate the stellar wind from the supergiant star, which can lead to a fluctuating accretion rate onto the neutron star. For 0114 plus 60 plus 65, the superorbital variability is attributed to these tidal oscillations. This is a very special system. It is one of the systems which has the longest orbital period amongst this list of supergiant HMXBs that we have. And it's also a very slow pulsar. So the conditions in this system might make it possible that the tidal oscillations could lead to the structured stellar wind that we see, which might cause this the superorbital variability. And tidal oscillations are predicted for circular orbits, which is the case for many of this short orbital period system. But they are unable to account for the transient natures of this modulation or the fact that we do see a strong second harmonic for many of these supergiant high mass X-ray binaries. The other prominent model is the presence of co-rotating interaction regions in the winds of the OB supergiant stars. So what these CIRs mean is there is an overdensity present in the supergiant winds, which is characterized by a spiral shape density and velocity structures. And whenever the neutron star crosses the CIR, the beating frequency between the frequency of the CIR and the neutron star, the orbital frequency, is thought to cause the superorbital modulation. And that is how these modulations are tied to its orbital period of the system. And these large-scale structures are thought to be caused due to irregularities which happen on the surface of the companion star, which could either relate to a dark spot or a star spot being formed, and that leads to this spiral shape density and velocity structures. So this is an animation by Emma, who is a student at the Maryland Institute of College of Art, and she is an animator. And she had interned with Robin last summer, and she came up with this schematic animation of how the CIR would look present in these systems. So this is for a single CIR crossing. If we think that there are multiple CIR, or at least in this case, double CIR presence in the system, this is how we would imagine the interaction to happen.
2 minutes.
So what we assume is if we have one CIR present in the structure in the supergiant stellar wind, the top panel there would be how the simulated light curve or the superorbital intensity profile would look. We would see a single peak, and depending on when the interaction happens, this peak could either be broader in nature. So what we see in the right panel is for 16418, there was this one particular set of time frames where there was only the fundamental which was present in the dynamic power spectra. And we do see a single peak structure of this superorbital intensity profile. But if there are two CIRs present in the stellar wind, it could lead to this double peak profile that we see in many of the time frames where there is both the fundamental and the harmonic present, or the harmonic present. So in conclusions, we think the superorbital modulation in supergiant high mass X-ray binaries could arise from the structure of winds in the OP star. Both the peak at the fundamental frequency of the modulation and its second harmonic are present in many of these systems, and they are transient over different time scale of years. Unfortunately, when the NuSTAR observations were carried out, the superorbital modulation had weakened, and that's why we do not find a difference between the predicted minima and maximum observations. What we think of the results is there might be multiple CIR present in the stellar wind of the supergiant, and that could give rise to this the presence of both the peak at the fundamental and the second harmonic, as well as its transient nature. However, the tidal oscillations cannot be ruled out. And there are a lot of unknown factors in terms of what we know about these long-term stable structures in the wind. And for that, we need more data, more observations. So optical observation of the CIR, NuSTAR observation when these modulations are present, and also find more systems where these modulations, the superorbital modulations are present. Thank you.
All right, do we have any questions? I have a question. We have your little list of superorbital modulations in the supergiant high mass X-ray binaries. There seem to be the superorbital periods were like quite consistently 3 to 4 times the orbital period. Is that significant?
Yes, so we do find them to be of the order of 4 times the orbital period. And first we thought because many of the systems have eclipses, maybe it's the aliasing effect, but we did account for that. And that seems to be the case for most of the system that we see. It could be tied up to the presence of the co-rotating interacting regions and the formation, and we only detect the systems when they are present and are and interact with them. So all of this could tie up to the fact that we only see modulations 4 times its orbital period.
Right. And a question over here.
Okay, I guess I have 2 questions. First, is there any energy dependence of the superorbital periods? So do they only show up, do they show up stronger in higher energies, or have you checked to look at different?
So they are there for, so we only see in SwiftBat 15 to 50 kV, and we do not see for 5 of them in the ASM band.
Okay, and I would imagine with SwiftBat, you might not have the statistics to do any better energy dependence with that. And then my second question, I guess, is related. It looks like you got really unlucky with the NuSTAR observations. Were those target of opportunity observations? And if not, are you planning to do targeted observations in the future?
Yeah, so those were geo observation where we asked for, we didn't ask for a TOO, but a guaranteed regular monitoring observation. And it was because when we wrote the proposal, the modulations were present. Mm-hmm. And it has been present for 5 years. It just so happened that when the observations were carried out, they just decided to vanish.
Yeah, that looked really unlucky.
Yeah, but now we are getting better in trying to predict when these modulations come back, and our next set of observation strategy is dependent on seeing certain features. If we see the spin modulation, the spin period change happening, or some other things happening, only then we trigger the TO.
Awesome, thank you.
All right, let's thank Nazma again. And welcome our next speaker.
Sorry, I have a quick announcement. If someone wants to come to the social dinner and hasn't replied to the survey yet, please reply to the survey. There's the link on the Slack. Okay, we need to know how many people are coming. Thanks.
All right, well, next speaker is George Younes talking about magnetars.
Thank you, Anna. Okay. Okay, thanks for the organizing committee for allowing me to talk a little bit about the main science that I do, which is on magnetars. This should be considered really a shallow overview of NuSTAR science case for magnetars, and I try to include as many as possible. So if I've forgotten any of your science, so forgive me for that. Time is not on our side. So let me just start by showing you the one of our favorite plots in the neutron star domain, and that's a period PP dot diagram. And so just a quick note on those that are not familiar with this. So on the x-axis, you have the spin period of a given source, and on the y-axis, you have the period derivative. The black dots are rotation part pulsars. They're the majority of the sources we know of. And then in magenta, you have accreting millisecond pulsars. Basically, these are recycled ones. And then the ones that I'm really interested in are the ones in red squares. These are the magnetars. So typically, magnetars are actually kind of discovered and considered magnetars from their magnetic activity. But every time we discover one, which is typically once a year, so that's the rate, and it's been stable for the last 10 years or so, since we have Swift up, they seem to fall in that corner. And so they have spin periods of about a few seconds, and it's a large spin down rate of about 10 to the negative 11. And so you can correlate these two parameters in order to infer the intrinsic properties of these sources, assuming the typical dipole magnetic radiation. So you can get the magnetic field of the source, the dipole field strength, and typically it falls around the 10 to the 14 Gauss for magnetars. Their spin down age is about few thousand years, up to 10,000 years or so. That's on average. And their spin down luminosity is about 10 to 32, 10 to 33. So quite small compared to rotation part pulsars. And this is a nice SED from one of the brightest magnetars, the Galaxy for UO142. So on the x-axis, you have the energy going from 0.5 all the way up to Fermi-Lat energies. And it's shown in UF new space. So you can see immediately two components. This is kind of a defining property of the spectrum of a magnetar. If you see something like this, then you have a magnetar at your hands. So it's a quasi-thermal. Sorry, I can't see my cursor here, but I don't have a pointer. But anyway, you have the quasi-thermal component between 0.5 and about 10 keV. And that's typically thought of as the surface heat, basically, from the decay of the magnetic field. And then you have another component that was discovered in 2004 from Integral RXTE, and later on, Suzaku discovered a few more in a few other sources. And that one is really shooting up in power, and it extends all the way up to 200 keV. Sometimes it's fully pulsed as well, 100% pulse at 200 keV. So because they are shooting up, we should have actually detected them already with CGRO and COMTEL. These are 2 sigma upper limits on that source. And because they're not detected, there's basically a break somewhere over there. Oh, this is fantastic. So you're expected to have a break somewhere over there. And the break is supposed, we are expecting it to be super exponential. So this is the SED, and we hope COSY will be able to actually detect that peak somewhere. So in some sources, we're missing indeed the peak of the SED. But magnetars are not only persistently emitting sources, they go through a range of activity, and that range of activity varies on timescales from milliseconds all the way up to years. So on millisecond timescales, what you have is what we call the short bursts. So this is an example of one. This is time in seconds from a Fermi trigger of SGR 1935 plus 2154, the FRB emitting magnetar. This is the count rate. And so it lasts about 200 milliseconds on average, could be anywhere from 10 milliseconds to about a second. And their peak luminosity is somewhere between 10 to the 37 and 10 to the even 42 ergs per second. So they're hyper Eddington by quite a bit. Typically, when we see these short bursts, and they can happen as one-off or even in burst storms where you see 100 in about 10 minutes or so, they are typically accompanied by an X-ray outburst. Occasionally, they show also radio. That's when the source is very interesting. And now we know sometimes FRBs, and that's when the whole community blows up. But and these outbursts are typically, well, prior to NuSTAR, they were seen mainly in the soft X-rays, where you see the X-ray emission climbing up by a factor of a few, all the way up to 3 orders of magnitude or so. And these also occur around times of timing anomalies, typically glitches or a lot of timing noise. So all of that range of activity obviously is connected to the decay of the magnetic field. So this talk is really purely observational. It's just one quick few words on the theory, just to put things into perspective. So what we're dealing with here is really an isolated neutron star with super strong magnetic field. So the modeling of it is you need to take into account the geometry of the system, rotation axis, magnetic field axis to rotation axis and the line of sight to rotation axis. You cannot do things phase average. It's a bit too simplistic. And you have to consider the fact that you have a twist in the external magnetic field, and that's because the decay of the magnetic field puts a lot of stress on the crust. And it's too strong that it actually, the crust yields under the stress of the magnetic field. So a twist, you have a crustal motion, and that twists the external magnetic field. So you have a twisted field loop. It doesn't have to be the dipole, and we know actually it's in many cases it's not the dipole. So that's adds another layer of complexity. And then you have to take into account the radiative processes and high B field regime. So in this case, what you have is soft X-ray photons from return currents in this twisted field loop that are inverse Compton scattered in the accelerated particles in this twisted field loop. And that's what gives rise to the hard X-ray tail. And that's what I'm focusing on here. But the inverse Compton scattering is resonant at the cyclotron frequency. So it can boost your energy by a couple of order of magnitude compared to the classical case. And then you need attenuation because you don't see these peaks at CGRO MEV limits. So the attenuation is photon splitting and single photon pair creation. So that needs to be taken into account. Anyway, the theory is actually evolving quite a bit, but we're slowed down because our theorists are busy dealing with FRBs, so we don't have any theorists. But for a different story. So prior to NuSTAR, what do we have? We had obviously Suzaku, Integral, and RXTE established the existence of these hard X-ray tails. However, many questions emerged from their discovery in 2004. And the questions range from what are the detailed spectrotemporal properties of these hard X-ray tails? So basically, are they pulsed? Okay, yes, we know that. At what level? Is it always 100% pulsed? And is the pulse phase aligned with the soft X-rays? Is it not? These type of questions. And then if you have a population of those sources where you detect the tail, are there any correlations with the intrinsic properties of the population, spin down age and magnetic field strength and so on? Are the tails transient? So in the transient sources, the transient magnetars, where the soft X-ray emission increases by a factor of 100 or so, do you see the same thing going on at the hard X-ray tails as well? Lastly, do hard X-ray tails appear during magnetar-like outbursts from non-canonical sources like high B pulsars? So those also have seemed to show magnetar-like activity. And all of that has implications on the radiative processes, high B field regime, crustal and magnetospheric dynamics, and so on and so forth. All right, so let's go to NuSTAR. I'm going to just kind of keep up with the story today, a lot of spectra. So these are a bunch of NuSTAR spectra of some of the sources. So the highlights here, for instance, are the detection of hard X-ray tails in sources that we did not know there was a hard X-ray tail simply because we did not have the sensitivity. So that case is 1E2259, for instance. A very hard X-ray tail in a transient magnetar 1547. This one actually persisted after the source went into outbursts. It's still there, in fact. I'll talk about it a little bit later. And then SGR 1806, this is a famous one that emitted the giant flare. It has one of the strongest hard X-ray tails. So if you look at this collection, you can see already a lot of differences among these hard X-ray tails. In 1806, it's dominating everything all the way down to 3 keV. In 2259, it's dominating all the way only up to 10 keV or so. And so now we can actually kind of probe whether there are any correlation among the population. And if you look at one of the strongest correlations is let's say the flux in the hard X-ray tail divided by the flux in the soft X-rays is a function of the characteristic age. And this is one of the strongest correlation that we find in the population. And it's expected in the let's say twisted magnetosphere model because at the early stages, that's when you have a stronger decay of the magnetic field. That's when you are going to move the crust quite a bit and create these twisted fields, and probably globally at the early stages of the magnetar life. And so that's why you have very strong hard X-ray tails at young ages. So this is good to see. There are other correlations that make things a little bit more complex, but let's keep it positive today. So I'm going to highlight just one case. This is work that is being currently done by my student, Rachel Stewart. So this is for 1708. I haven't shown it before, but to give you an idea of the details that you can do with NuSTAR. So this is a light curve from NuSTAR and the simultaneous XMM Newton observation. This is the phase averaged spectrum. So you can see the typical quasi-thermal spectrum below to 10 keV and the hard X-ray tail extending all the way up to 70 keV. And just to give you a level of detail, this is the pulse profile as a function of energy. So at first it's single peaked up to about 2 keV. And then there's another peak that starts emerging at about maybe 3.5 or so. So it becomes double peaked. And this is the RMS pulse fraction as a function of energy. So basically the RMS pulse fraction of these. And then when you get to 35 to 70, it's purely single peaked. And the peak obviously has shifted by about 0.25. So all of that will correlate with your theoretical expectations, especially the geometry of the system. This is actually a paper that should be submitted pretty soon by one of my collaborators, Zarawa Bodyasan. And all I want you to focus on is the theoretical curves in green. This is the total intensity as a function of the geometry of the system. So you have alpha, the angle from the rotation to magnetic moment axis, and then line of sight to rotation. And the psi 65 with alpha 65 degrees, they will give you this curve that looks pretty much similar to the pulse profile that we have at high energies. And this geometry of the system actually correlates well, or in fact, pardon me, it's consistent with the geometry that we get by other means for the same source, which is great. We are very confident in the geometry that we're probing for the system. These are very important parameters to know. So let's move on to the transient magnetars now. So I'm going to start by talking about the radio quiet ones before we delve into the radio loud, just to see if there's any differences between the radio quiet and the radio loud magnetars in terms of their hard X-ray tails. There are many cases, and again, the hard X-ray tails vary from source to source. So for instance, in 1935, SGR 1935, the hard X-ray tail emerged after the 2016 outburst. In fact, after the 2014 outburst, when the source was detected, there was no hard X-ray tail in this case. In 2016, it emerged, and I will show you later, it's actually persistent, and it's continuing to be visible to us 5 years later. This is the case of 1048. This is one. This is quite a bright magnetar, soft X-rays, never showed a hard X-ray tail, and then an outburst, you have this beautiful hard X-ray tail that emerged. Same thing for Swift J1555. And then you have the cases where you have very weak hard X-ray tail, like the case of SGR 1830 -645. So that gives you again the idea that it's not a universal thing. It probably depends a lot on geometry and location of the triggering and all of that. So it's quite a complex thing. And moving on to the radio loud magnetar. So here I'm showing 3 cases. So the SGR 1745 -2900. This case is actually quite unique because NuSTAR was the one that confirmed the magnetar nature of the source by detecting the pulsation and the spin down rate. So this is the radio loud magnetar, the galactic center one, and you can see the hard X-ray tail extending all the way up to 70 keV. This is 1E1547. So this is again a curious case in the sense that you have this nice hard X-ray tail that was detected, I believe, after 2009. It was a lot softer before that. And then it basically persisted all the way up to about a month ago. And the interesting thing about this is that about a month ago, also the source showed this kind of a weak outburst, let's say, when the radio turned off, because this is a radio pulsar continuously. So the radio turned off for a couple of weeks, and then it turned back on again. But it seems that the hard X-ray tail did not really quite care about what was going on. But you can see the increase in the soft X-rays by about 60% or so. And lastly, obviously, SGR 1935 plus 2154. So I actually lied before because I told you it was radio quiet, but that's what we thought until October 2020. And then in October 2020, it was detected that the radio pulsar was fast. And so we had an observation during the time of the radio pulsation detection. So in October 2020, and you can see pretty much exactly the same hard X-ray tail that you saw from before. So again, in this case, actually the radio turned on, yet the hard X-ray tail did not change from before. So it seems like they're really, truly not correlated and completely two different regions. And again, very likely, whether you turn on one or another. 5 minutes? Oh, plenty, thank you. And moving to the transient magnetars that are, continuing, sorry, with the transient magnetars that are radio loud, I will talk about the ones where you do not detect a very strong hard X-ray tail. So XCE J1810. This is the first transient magnetar that was discovered in 2003, I believe. As well as Swift J1818, which was discovered in 2020. And in these cases, both of these cases, especially Swift J1818, there's a very weak hard X-ray tail that's to be compared with the previous slide, where you had these booming hard X-ray tails in 1935 and in 1547. And yet it seems that this does not quite matter. The radio pulsations were detected in both cases. So this was the same conclusion for the radio quiet magnetars. If you recall, for the radio quiet, SGR 1830 did not quite have a hard X-ray tail, but the rest showed a prominent hard X-ray tails. And so it seems truly that we're starting to understand what's going on in the sense that these two things are not truly correlated. The hard X-ray tails are very likely due to inverse Compton scattering and closed magnetic field lines. And if this is, and it's very likely pulsar-like, this radio emission is coming from open field lines. And depending on what you actually activate, so where your triggering mechanism is on the surface of the magnetar, whether it's connected to the open field lines or connected to only the closed field lines or both together, that's when you are going to get radio emission or hard X-ray tails or both together. So this is the only way we can see this playing out. And so lastly, moving on to the rotation-powered pulsars that turned magnetars. So this is a case of PSR J1119. These are very interesting cases because they kind of connect the isolated neutron star population together. And there's a big push in order to kind of create a whole family and understand them evolutionary. So, and these do indeed bridge the gap between rotation-powered pulsars and magnetars. So in the case of PSR J1119 minus 6127, this is a GeV, high B, radio RPP, so it shows radio pulsations and GeV pulsations in Fermilab. And in 2016, it went into a magnetar-like outburst where it showed typical short bursts. These were seen, I believe, with NuSTAR and XMM. And there was the emergence of a hard X-ray tail, exactly like you would expect from a magnetar. It was a weak one, but still there. And the pulsations were seen up to 20 keV. The interesting element about this radio pulsar is that in the first couple of weeks, when the hard X-ray tails emerged and the source went into outburst, showed short burst, the radio pulsar emission turned off, and then it emerged more magnetar-like and not really pulsar. And that depends on the spectral shape of the radio behavior. So that's kind of interesting, telling you perhaps that the magnetar activity is not really compatible with radio, purely radio pulsar, rotation-powered pulsar activity. And more so, the interesting element is that during the 3 short bursts that were detected by NuSTAR, the radio emission just simply turned off exactly at the time of the 3 bursts. So, so it's happening at long time scales over weeks at the beginning of the outburst, but also during short bursts, you can shut off that radio emission for about 70 seconds or so. And the other high B rotation powered pulsar is PSR J1846, pardon me. So this one is not a radio pulsar, it's actually MEV peaked. So the peak of the SED is in the MEV range and not in the GeV range like the one before. And it went into outburst in 2020, and there are NuSTAR and NiSTAR observations that are close to one another. And if you look at the broadband spectrum, you can see that the green and the blue lines are in fact the broadband spectrum from after the outburst finished. And you can see this hard X-ray spectrum, but this one actually kind of continues into the MEV range, going back into a rotation-powered like spectrum. However, during the outburst itself, in the first couple of weeks, that hard X-ray tail became a lot softer, and kind of a thermal pulsed component showed up in the spectrum. So again, it doesn't have to be radio. It seems like the rotation-powered emission, whatever it is, in this case it's MEV, it's not compatible with magnetar-like activity. So I'll finish with that. Looking ahead, really NuSTAR has opened a window for a better understanding of the magnetar lab itself. And we're only scratching the surface with the data. Really, we have a lot. But few facts are established that bright, persistently emitting magnetars generally show strong hard X-ray tails. Not so much for transient magnetars, but not all of them. That's not all of them. And there's no correlation with the radio emission. That's quite an important element, I would say. And the magnetar emission not compatible with rotation-powered pulsar radio emission. That's also something for the theorists to think about. And looking ahead, I look forward to a combination of COSY and NuSTAR observation of some of these sources, and even further ahead, looking forward to some HMXB contribution to the field. Thank you.
All right, we have a question from Slack from Kayamori again. Do people generally fit a power law model to the hard X-ray components of magnetars? Since thermal X-rays from the surface are upscattered in the magnetosphere, would fitting some kind of convolution model be linked to the soft ray X-ray emission be more appropriate?
Yeah, so the work that is being done by Zoravar is really taking the soft X-ray emission from the surface and then upscattering it in the magnetosphere. I'm not sure if Kaya that's what he meant, but indeed, you're taking a thermal emission from the surface and upscattering it in that magnetosphere. So it's becoming more and more complicated, far away from really comparing with data, but we're slowly getting there.
Great. We'll leave any further questions on that to Slack. And yeah, let's thank George again and welcome our final speaker for this session, Edward Nathan.
Right, thank you. So hi, yes, I'm Ed. I'm a PhD student at Oxford, finishing up soon with Adam Ingram. So I'm just going to talk to you about some of my work recently, which has been a proof of principle mass measurement of the black hole in the X-ray binary 81743-322. So just a basic summary of the X-ray spectrum we see from such systems. So there was a thermal disk or a quasi-thermal disk kind of spectrum. As the accretion disk gets hotter towards the central object, the black hole, it gets hotter, producing that kind of X-ray, multicolored X-ray spectrum. We also then, of course, see the corona law, the corona power law, going from kind of the seed photon energy up to the electron temperature energy. I see that directly. But importantly, we see some of those coronal photons reflecting off the accretion disk. So as was briefly mentioned, there are a lot of sharp features in this reflection spectrum in the local disk rest frame, but we see this having undergone a lot of relativistic effects. So particularly Doppler boosting, Doppler shifting, and that will come from all across the accretion disk, which all have their own kind of relativistic situation, depending exactly where it is. So we see this reflection broadened out, and the exact shape of this reflection spectrum does trace the kind of inmost geometry of the accretion disk, and as I said, it does trace the kind of innermost regions of the accretion disk, which, although in this case that is not necessarily the ISCO, the disk may be truncated beyond above that. So the reflection spectrum, particularly in its local frame, is also known to be dependent, well, for a long time, on the ionization parameter, which is related to effectively the flux onto the disk and the electron density within the disk. However, in 2016, Javier showed that this also depends not just on the ionization parameter, but also the disk density itself. So this is a figure from his paper, where you see a lot of differences, but even within the NuSTAR band, you can begin to see that there are some differences there. We can begin to use that. And in fact, there have been recent papers, recent studies, which using reflection modeling, which show that reflection models can constrain both the ionization parameter and the disk density separately. The point, though, is that if you've got both of those, you also can just use that to constrain the flux on the disk. So, as a paper which was introduced was introduced by Adam Ingram, paper, probably guess this, early this year. You point out that if we know that the size and the kind of size of the disk, at least in terms of gravitational radius, so proportional to the mass, if we know that, and we also know the flux onto the disk, that means that we know the illuminating luminosity onto the disk, at least in terms of units proportional to the gravitational radius and the black hole mass. So, and if the disk is optically thick, and we can assume that all the illuminating kind of luminosity is emitted as reflected luminosity, we can then compare that, what we know the luminosity here, with the flux that we see, which of course is just dependent on distance squared. And we can put all this together, and we can use this to kind of then constrain at least the mass to distance ratio, black hole mass and the distance ratio of the source. So this was presented originally in terms of looking at AGN, but the same principles apply to X-ray binaries. In particular, I think the paper also suggested that you can use timing information as well to try and break the mass distance degeneracy, or if you know through scaling relations, you might have an idea of the mass. But either way, this holds to some extent, at least. So what have I been doing? So I've been looking at the black hole X-ray binary 817-43-322. Now this is one which has undergone many outbursts, particularly in 2014, 2016, 2018. We do know have a rough distance measurement, about 8.5 kiloparsecs, which should sound very familiar, given it is consistent with being in the galactic bulge. Of course, there's an error on that. That was work by Jack Steiner, 2012. And also, again, kind of consistent with it being in towards the galactic bulge. The source is highly extincted, which means that there is no optical dynamical mass measurement for it, because we can't make that. So we don't know what the mass is, which is why this method is potentially quite interesting. So I looked at some five epochs of data, which cover 3 outbursts, all of these kind of in the hard state, 2014, 2016, 2018. So I had 1 observation from 2014, then 2 from each of 2016, 2018. I was looking at simultaneous NuSTAR and XM Newton data. However, the XM Newton only had the RGS and FPN in timing mode available, and the calibration between XM Newton in timing mode is not brilliant with NuSTAR. I did look at the recent, I know there's been a recent calibration release, which is meant to work a lot nicer with NuSTAR. That I can get that to give me, in theory, better results, closer results, but still not great. If anybody has any tips with that, do let me know, because of course that will help. But anyway, I looked at it, first of all, these 5 epochs individually, just taking our model, fitting it and seeing what we got. Then I also looked at them together. So loads them all up in one. And the only thing I really assume are the same are, for example, the black hole mass to distance ratio. I assume that the inclination source and also the iron fraction in the disk is the same between all epochs. Apart from that, I kind of let everything go. I did some fitting, and then to get an idea of what was going on, I ran an MCMC. So for individual fits, I did that for the individual big joint one. And I looked at some Bayesian priors, which helped constrain some of the parameters in the model. Particularly, so this method is it requires actually that we know the flux that we see. So if you have the kind of efficiency from NuSTAR, that is kind of a normalization parameter, but we also know there's an uncertainty on that. So you put that in as kind of Bayesian prior. We can also then constrain the mass by using the known kind of prior on the distance. So that was the approach that was taking. So what we got? So massive disclaimer. There are a lot of parameters in here, a lot of data. This MCMC is taking a very long time to run, and it's still going, and it's slowly getting better. But okay, the top ones up here is each of the individually done MCMC. We can see that at least for 3 observations, it's a bit more constraining than, for whatever reason, 2018 observations or less. But when you put them all together, it's beginning to come out with a mass of around 12.1. And this error has been growing on this, and it's beginning to look about like it might be settling down now. So hopefully that's going to be close to the final result. which is quite nice. So if we compare that to some black hole mass populations of black hole binaries, we found that it's slightly higher, but not inconsistent with population produced by Earnshaw in 2010. And I put out that it's definitely not the first black hole that has been found as a higher mass in that distribution. Put out CX1. I know that's slightly different, but it came out that's a high mass. And also, we also know that gravitational wave events are also indicating higher mass black holes. So that is potentially interesting. This could be an interesting link. So I know my paper, Yonketel 2021, considering these kind of, particularly I think the gravitational wave population was different to X-ray binaries. And he kind of pointed out that dynamically confirmed black holes tend to be found in tend to lie in regions of galaxy where they may be less likely to be formed. So if here's a figure slightly rearranged from this paper. So under this black line is it kind of indicates that that's where they expect more massive stars to be formed, which are then likely to produce kind of black holes. But at least in orange, the massive in orange, the dynamically confirmed black holes, that's kind of where they're located. So he suggested this could be to do with potential kicks. For various reasons, large black holes may be receiving smaller kicks, which then put them into this area where we can then observe them because they're less extincted. I've kind of flashed on where this is roughly looking for 1743 in this orange star, and you can see that it's going to, so in blue here, the non-confirmed ones, and we're beginning to maybe probe some of these things. So if this method is working, which it seems to be, then we can begin to use it for X-ray binaries, which we can't otherwise measure the mass for, which is good. So considering implications of this particular source, so there was a paper by Jack Steiner who used the radio jet observations to try and measure the distance that we're using. And he also uses kind of soft state observations to measure, to begin to try and look how to handle the spin of a black hole. Now, this was done assuming the Earth's distribution, which is around here, which gives you this kind of close to zero-ish value, 0.2 plus minus 0.3. If my results are accurate, then put up here, which might be indicating slightly higher spin for the source, which could well be interesting. Now, you have heard me say if a lot, potentially. There is a few caveats, of course. So one of them is disk density. So in the model, the density is roughly proportional to the inverse of the mass, very approximately. So, and we're also finding our models are requiring quite high densities in the FITs and the MCMC. So, and using silver models, which kind of at the moment are reliably capped about 10 to the 20. So we are running up against that quite a lot, which is potentially means we're undersampling the lower masses. So maybe that's just where that's coming from. So we're just going to put some conclusions up that this method does seem to be working, is giving us a relatively sensible result. It definitely needs further testing, particularly, of course, the obvious thing to do is look at a source with a known mass, apply this and do that. And of course, you can then bring in, for example, the timing, kind of timing things, vibration mapping, and be able to break the mass distance generally with that. However, the black hole in the system may be generally a bit more massive than current population estimates, which could easily be due to kind of observational bias about the heavier sources are less likely to be moved into a less thin part of the galaxy. But if the method, if trusted, would allow us to measure the mass of candidate black holes in closer to the galactic plane, which could then help probe that potential population. But also, finally, the black hole, as I said, might have a slightly higher spin than we thought if it has a higher mass. So yeah, so I'll leave it there. Thank you.
All right, any questions for Ed?
Yeah, thank you for a really interesting talk. So one thing I was interested in, so to get the mass out from the reflection spectrum, you need to put a physical size scale in. which you're doing from the ionization of the disk as a proxy of the flux it receives. So I was wondering, how sensitive is your mass measurement to assumptions you're making about the geometry of the X-ray source? Does it need to be a point source in your model, or are you insensitive to that?
Okay, exactly. So I'll just skip back to this. So this model at the moment is using generally the kind of lamppost model that I've kind of sketched onto here. It possibly is going to be that kind of thing. That kind of thing is going to be important, and I think it's generally found that this kind of geometry does work. It's not necessarily perfect. It is, of course, going to be open to a lot of some of these assumptions. Yeah, I think what I'm kind of not trying to say necessarily that I've got an absolute mass measurement. There's going to be errors, various systematic errors, which are going to dwarf the kind of system errors that we're finding. So yeah, I think ultimately yes. Yeah, the answer is yes. It depends how much you trust kind of the geometries, and that makes sense. But we have to start from somewhere.
Sure thing. Thanks a lot.
Yes.
All right. Well, the Slack channel remains, so feel free to continue asking questions and discussing that. But for now, let's thank Ed and all our speakers again. I'll hand off to Christian.
Murray, do we have you online?
Yep, I'm here. Can you hear me?
We can. So I think that's great. Well, let's start then. Go ahead, Murray. You go in 1 minute. I'll start clapping when your minute is up.
Okay, so yeah, this is my poster about a new ULX that we found in the galaxy NGC 4045. I found it by I was actually looking for transients by searching through Swift XRT observations. Swift was actually looking at an optical transient called 2019 WVG. I think it's a supernova candidate. That source wasn't detected, but what we saw in the other side of the galaxy was a new X-ray source. We continued monitoring it with Swift. It turned out not to be a transient in the end. It looks like just a highly variable source. And the first thing to note was that it's actually peaked above 10 to the 41 ergs per second. That makes it a hyperluminous X-ray source. So that these are pretty rare sources. They only constitute about 4% of the ULX population. We got some follow-up observations with XMM and NuSTAR. And
great. Great. Lovely. Sorry, moving on. Next.
Can you hear me?
No, we can't quite hear you.
And now?
But
okay, thank you.
Yeah, here we go.
Hello,
Go
everyone.
ahead.
My name is Sergey. I'm from Max Planck Institute for Astrophysics in Garching. My poster is devoted to the study of the X-ray pulsar V0332 with the ERXT observatory. We found the long and short-term variability in the iron line emission equivalent bits and also the co-absorption edge. The most interesting result is that the co-absorption edge varies as the pulsar rotates and peaks during the dips in the light curve. So we discussed the results in the framework of the current X-ray pulsar systems. Sorry, yeah, that's all.
Ooh. Next up.
Okay, hello everyone. My name is Ben Kogenauer. I'm at Space Sciences Lab at UC Berkeley working with John Tomczyk. I do have 2 posters, so I get 2 minutes. First one is about MaxEJ 1803, which is a new transient black hole X-ray binary that went into outburst in May of last year. A couple different NuSTAR observations. The one we're taking a look at is in red, clear reflection spectrum that we can fit with high density models. I think the main takeaway, we were hoping to measure the spin of this source, but instead we kind of show that the high density models are required to sort of bring back things we know. It's a dipping source, so we're able to get a good measurement of the inclination. And feel free to come up to my poster or talk to me about that source. How'd I do on time?
You're good. Okay. You want the next?
Yep. So the next one is a totally different area. Aaron was nice enough to show one of these spectra in his talk earlier today. John and I have been working on following up integral hard X-ray detected CVs or candidate CVs to be sure that they are either CVs, and if they're magnetic CVs, looking for a period detection. These two sources, J18007 and 15038, we were able to catch the spin period of both sources, confirming that they are IPs, and then measuring the masses was the next goal, which NuSTAR is sort of uniquely able to do with the high energy ability. One thing that's unique about our study with these two sources is we're taking into a ton of detail and trying to, as rigorous as we can, using the XMM and NuSTAR spectrum, model the entire continuum in order to get our mass measurements. So that's something we've taken into account. On the right is just Earnshaw's sort of legacy NuSTAR IP spins and masses. And it sort of shows that the ones we're picking out from integral tend to be on the high mass side. And that's it. Thank you.
Perfect timing. And next up.
Hi, I'm Sachin Das. I'm a PhD student at the University of Leicester working with Simon Vaughan. My post is on our Bayes analysis of max J1820, which you can see a visualization of there. We used 3 XMM Newton and 2 simultaneous NuSTAR observations from March and September 2019. Fitting this with 0 spin model and a non-truncated disk. We also have a high spin variant of that. And we adopted a fully Bayesian approach with priors on distance, inclination, mass, and a bunch of others, including those from accurate modeling of the interstellar medium absorption. Yeah, thank you.
Next up, we have Robotka.
Yeah, me. Okay, hello. We are interested in categories and variable, which is a novel-like system. The systems, they are so full of category variables, and they spend majority of the time in a high state. Mass accretion rate derived from the optical observation should be 10 to minus 9 solar masses per year. We got XM Newton observation from because of different purpose. And our measurement of the flux or the mass accretion rate was 3 orders of magnitude lower. The explanation of this inconsistency is the presence of kind of X-ray hot corona, which is known from AGN and X-ray binaries. But it seems that we got the observation during the high state, but we don't. The real stable high state plateau started a few days later. So it's quite possible that the accretion flow was still under evolution during the time of our observation. So something independent it's needed. There are 2 observations in a real high state, that was Swift and NuSTAR, and both of them they yield like 10 to minus 11 solar masses, but blah, 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 please see our poster. Out of time, right? Perfect.
You guys are really good at this. Okay, next up is Hamza Elbiad. I hope I said that.
Hello everyone, I'm Hamza Elbiad, PhD student at the University of Cagliari. My poster is about the periodic X-ray variability in the M82 galaxy. Throughout 33 observations taken by NuSTAR, we have studied the variability of this group by fitting for each observation 3 power density spectrums. One of the full band energy and the others for hard and soft band energies. The fit was these energy bands were used to investigate the original source of the power of the quasi-periodic oscillation, and because NuSTAR is unable to separate the 2 ULXs. The fit were used with the maximum likelihood method and for parameter estimation, and the pulsar technique to improve the uncertainty.
Thank you. And next up is Jeremy here.
Hi, I'm Jeremy Hare, postdoc at NASA Goddard Space Flight Center, and my poster is a brief overview of high mass gamma ray binaries as seen by NuSTAR. You see them all listed there. They've actually all been observed by NuSTAR. Those are pretty rare sources. But the main focus of the poster is on one particular source called LS5039, where Younes et al. In 2020 found pulsations in the NuSTAR observation of this source. Then went back and looked at Suzaku observations and found pulsations in a similar place. And if you infer the dipole field from those difference in spin, you find it has a magnetar-like magnetic field. So we obtained a new observation of this source in 2022 with NuSTAR, and I presented the results of my poster. So please feel free to stop by.
Next up, we've got Vasilopoulos.
Hi everyone. So I'm Afia Zainab from the Eurosat network of the Eurosita telescope, and our goal is to use the Eurosita all-sky survey data in order to find X-ray binaries in our galaxy and then characterize them with follow-up observations. And I present here a follow-up analysis of 3 X-ray binary candidates. One of them was followed up with NuSTAR, and with its help and also lucky archival observations in the optical regime, we found that it is an X-ray binary with a B counterpart and likely a neutron star, but because we don't see any pulsations. And the other 2 sources were followed up with XM and Newton, and at the moment they behave similarly, but it's not super clear if they are actually X-ray binaries because they do appear to be more like chromospheric active stars. Nevertheless, this is still ongoing work, and the search for new X-ray binaries in our galaxy will continue on with the Eurosita data.
Next up, we've got, sorry, you get to say your name.
Armenia. Okay, my name is Armin from the University of Turku, and in this paper we actually present the results of detailed investigation of the probably studied XRP2S8045 based on the single NuSTAR observations obtained during the 2017 outburst of this source. As a result, unfortunately, we didn't detect any cyclotron line in phase average and phase result spectra. We also used other data from different X-ray satellites to study the evolution of the spectral parameters based on orbital phase, which revealed the high hydrogen column density for the source, reaching 10 to 24 per centimeter squared near preastron. We also did IR analysis and roughly classified the optical counterpart of the source to be an OB supergiant and some other stuff.
We're at 10 more seconds. Okay. And next up, we've got Jacob Stierhoff.
Yes, hi, I'm Jakob Stierhoff. I'm a PhD student of the University of Erlangen, and the poster I'm having here is presents work that's currently in progress on the XTE-J1859 plus 083, a source that was discovered in 1999 and only had 1 outburst in 2015. And we try to squeeze all the data we have to get most information. So right now we have reliable orbital parameters, and we are working on the pulse profiles in time and in energy space to get some geometry of the source. Thank you.
And finally, we've got Talhammer. It's a great last name. I love that.
Thanks. Yeah, I'm Philip Talhammer, also from the University of Erlangen. And we looked at the giant outburst of the B X-ray binary XC2030 that happened last year. And we got really nice NICER and NuSTAR data covering the outburst. And especially if you look at the NICER data, we really see a very clear transition in the pulse profiles, which you can see on the upper right corner, tracking some stark change in the emission geometry, which we also tried to model via ray tracing code, which worked quite well and allowed us to get some information about the accretion column geometry around the NuSTAR.
Thank you. That concludes the lightning talks for today.